Humanity did not need an asteroid to make the world suddenly feel smaller. In the year 536, the sky dimmed, harvests weakened, cold spread across regions, and entire generations were forced to survive inside conditions they could not explain. The deepest loss may not have been a single city or kingdom, but years of human possibility quietly erased before they could begin. Modern evidence is now sharpening that picture. So why was 536 AD called the worst year to be alive? And what have scientists recently found that changes what we thought we knew? Before the sky changed, most people living across Europe, the Mediterranean, Western Asia depended on a rhythm far older than any kingdom. The year was measured not only by calendars or rulers, but by light, temperature, rain, soil, and the return of growing seasons. A farmer could live under the authority of an emperor, a king, a bishop, or a landowner, yet the most basic conditions of survival still came from forces no government could command. Grain needed enough warmth to mature. Animals needed pasture. Rivers had to remain useful for transport and irrigation. Even cities that seemed distant from farming were tied to fields beyond their walls, because urban populations could not eat without a movement of food from countryside to market. This dependence continued a relationship that had shaped our species since long before permanent settlements existed. Earlier human communities adapted to changing environments through movement, flexible diets, and knowledge passed between generations. Agriculture created larger settlements and concentrated populations, but it also bound many communities more closely to landscapes and predictable seasons. By the 6th century, that relationship had become complex. The Eastern Roman Empire connected farms, ports, roads, armies, and cities across the Mediterranean world. Farther north and west, political authority was divided among different kingdoms and communities, each with its own arrangements for land, exchange, and food. Across parts of Asia, states and societies likewise depended on harvests, livestock, waterways, and seasonal movement. These societies were not identical, and they did not experience environmental change in the same way. Yet beneath their differences lay a shared biological fact. Every human body still required energy that came from the living world. Sunlight supported plants. Plants fed people and animals. Harvests became stored grain, bread, fodder, taxes, trade goods, and reserves for months. When that chain functioned normally, it could become almost invisible. People planned journeys, military campaigns, household work around an assumption that the seasons would remain recognizable. That did not mean life was easy. The 6th century already contained war, political rivalry, shortages, disease, large differences in wealth. A poor household and a wealthy estate did not face the same risks. Some regions could import food when harvests weakened, while others depended more directly on nearby fields. Historical evidence is uneven, so we should not imagine a single average person whose experience represents an entire continent. Food systems also had limits. Storage could soften a bad season, but stored food was finite. Trade could move shortages from one place to another, but it could not create grain that had never grown. Political organization could redistribute supplies, yet it still depended on what farms, herds, fisheries, and markets produced. For thousands of years, humans had learned to live with ordinary variation in weather. A dry summer, a cold spring, or a damaged harvest could be serious without becoming a civilization-wide catastrophe. Communities responded by storing food, exchanging goods, moving animals, relying on kinship networks, or seeking help from neighbors and authorities. These strategies mattered because human survival has never depended only on individual strength. Cooperation, memory, and social organization are among the oldest tools our species possesses, but every protective system has a scale beyond which it becomes strained. People in the early 6th century could understand a failed crop, a harsh winter, or an unusual storm. They had inherited generations of experience with such events. What they were not prepared to understand was a disturbance that would alter the appearance of the sky itself and weaken familiar seasonal patterns across a wider area. Before that happened, there was little reason for an ordinary household to imagine that daylight itself could become unreliable. The sun rose, fields were prepared, seeds were planted, animals were moved, and communities entered another year carrying the same quiet expectation that had guided countless generations. The world might be difficult, but the basic rhythm connecting sky, land, food, and human life would continue. To understand why a change in the sky could become so dangerous in the 6th century, it helps to look at what survival actually depended on. Most people lived much closer to the production of food than people in modern industrial societies do. Even where large cities existed, the food eaten inside them had to be grown, herded, caught, stored, transported, and protected somewhere else. Grain was especially important in many regions because it could be dried and stored for longer periods than fresh foods, but storage was never unlimited. A good harvest created a margin of safety. A weak harvest reduced that margin. Several difficult seasons could turn a manageable shortage into a deeper problem, especially for households with little land, little wealth, or limited access to trade. The same basic vulnerability can be traced far back in human history. Our species evolved with the ability to adapt to many environments, but adaptation never removed the need for calories, water, shelter, and social support. What changed with farming was the scale of dependence. Once communities invested heavily in crops, fields, storage buildings, livestock, roads, and permanent settlements, survival became tied not only to nature, but also to systems built around nature. Those systems could be remarkably effective. They could move grain across long distances, collect taxes in kind, feed soldiers, support towns, and create reserves, yet they could only redistribute what the environment had allowed people to produce. The Eastern Roman Empire had administrative structures, ports, shipping routes, and commercial networks that could carry food through the Mediterranean. Other regions relied on different combinations of local farming, seasonal movement, exchange, tribute, and household storage. None of these arrangements should be imagined as equally fragile. Coastal settlements could sometimes draw on maritime trade. Pastoral groups could move animals when local conditions worsened. Wealthy households could buy food at prices that poorer families could not afford. But every response depended on time, distance, and available surplus. Grain could spoil, be lost, or become expensive. Animals needed fodder even when people themselves were short of food. A village that had stored enough to survive one poor year might have little left if the following harvest also failed. This is where the rhythm of nature and the structure of society met. A bad season did not strike every person equally. It passed through inequalities that already existed. A landowner with reserves, a merchant with access to distant markets, and a labourer paid in food or coin occupied very different positions when supplies tightened. Historical evidence rarely lets us reconstruct every household in detail, so it would be misleading to describe one universal experience. What we can say is that resilience depended on buffers: stored grain, livestock, trade connections, family networks, access to land, political support, and the ability to move. When several buffers weakened at once, the biological needs of the human body became harder to separate from economic and political conditions. Hunger was not simply the absence of food somewhere. It could also result from food being too distant, too costly, too difficult to transport, or too unevenly distributed. That distinction matters for understanding the 6th century. Civilization had created layers of protection between a person and a failed field, but those layers were not complete. Human beings still lived inside the same ancient energy system that had always sustained them. Plant growth became harvests and pasture. Harvests fed families, workers, animals, armies, and cities. When that chain remained stable, societies could absorb ordinary trouble. When it weakened across more than one season or region, the burden could spread through markets, households, political institutions, and bodies. By the opening decades of the 6th century, people had many ways to survive hardship, but none of those methods could guarantee protection if the environmental foundation beneath them changed in a way that was wider, longer, and stranger than the crises their communities already knew. The first sign that the familiar order of the year had begun to change did not arrive as an explanation. It arrived as an observation. Writers living in or near the Mediterranean world recorded that the sun appeared strangely weak. Its light diminished in a way that seemed unusual enough to remember. One of the best-known accounts comes from the historian Procopius, who described a period when the sun gave less brightness than expected. and the year seemed marked by an eerie reduction of normal daylight. His words have often been repeated because they sound dramatic to modern ears, but their real value is quieter. They show that something in the atmosphere was noticeable to people who had no modern instruments, no satellites, and no knowledge of volcanic aerosols. They could only compare what they saw with the sky they already knew. That distinction matters. A 6th century observer could notice that daylight looked wrong, that warmth seemed weaker, or that seasonal conditions were unusual, but could not measure the global scale of the disturbance. Nor should every report from the period be treated as if it described exactly the same event in exactly the same place. Ancient and medieval records were written for different purposes, by different authors, and often preserved through later copies. Some are more precise than others. The safest way to use them is not to force them into a single perfect story, but to ask whether independent descriptions fit a broader environmental pattern that can be checked by physical evidence. Even before that evidence is introduced, the human meaning of a dimmer sky is important. For most of our species' history, people learned the environment by watching repeated signals: the position of the sun, the return of warmth, the behavior of animals, the timing of rain, and the growth of plants. Those patterns were never perfectly stable, yet they created expectations strong enough to guide planting, travel, storage, and work. A change in the appearance of daylight, therefore, touched something more basic than curiosity. It disturbed one of the oldest relationships between human beings and the world around them. Still, we should resist imagining universal panic. The surviving texts do not allow us to know how most ordinary people reacted, what they thought caused the phenomenon, or whether every community even noticed it in the same way. Some may have experienced poor weather without ever seeing a written explanation. Others may have continued normal routines until changes in temperature or crops made the problem more difficult to ignore. What is significant is that the sky entered the historical record as part of a wider period of abnormal conditions. The year 536 did not announce itself with a clear beginning that everyone recognized. There was no message telling people that a major climatic disturbance had started. There were only pieces of experience: weaker sunlight, unusual atmospheric appearance, altered seasons, and later the consequences that followed through fields and food systems. This is often how large environmental events are first experienced by human beings. The cause may be distant and invisible, while the effects arrive locally, one ordinary observation at a time. A farmer sees growth slowing. A traveller notices a pale sun. A household uses more of its stored food than expected. A chronicler writes down something strange because the sky no longer looks familiar. Long before modern science could connect these fragments, people were already living inside the event. That uncertainty is central to what made the moment historically important. The people experiencing it possessed memories of ordinary bad years, but they had no framework for recognizing a disturbance that could reach far beyond one valley, one kingdom, or one farming season. The scale remained hidden even while the symptoms were becoming visible, and the most important clue was above them, visible every day, yet still impossible for them to fully understand at the time. For people living through the year 536, the most unsettling change may have been visible before its deeper consequences could be measured in fields or food stores. The sun itself seemed different. Procopius, a 6th century historian writing about events in the Mediterranean world, described a sun that gave light without its usual brightness, comparing its appearance to the moon and noting that this condition persisted for an extended period. Another writer, John of Ephesus, also recorded an unusual dimming of sunlight during the middle of the 6th century. These accounts are important because they came from observers separated from modern climate science by many centuries. They did not know about sulfur aerosols in the upper atmosphere, radiative forcing, or the chemical traces that would one day be extracted from ancient ice. They simply recorded that daylight no longer behaved as expected. The safest way to understand these texts is not to treat every phrase as a precise scientific measurement. Ancient writers used the language available to them, sometimes mixing direct observation with interpretation, religious meaning, or literary comparison. Yet the repeated description of weakened sunlight becomes more significant when placed beside physical evidence discovered much later. What a person standing outdoors actually saw probably varied with location, season, weather, and the thickness of material in the atmosphere. We should therefore avoid imagining one uniform grey sky stretching over every inhabited region at every hour. The historical record cannot support that picture. What it can support is something quieter and more unusual. In several surviving accounts, ordinary daylight became strange enough to be remembered and written down. For a society whose daily life depended on natural light, this was not a small visual detail. Work began and ended with the day. Farmers watched the sky because warmth and weather mattered to crops. Travellers depended on familiar environmental rhythms. People had lived beneath the same sun for countless generations, long before farming, cities, writing, or empires existed. Human vision, sleep, activity, and seasonal behaviour developed under a world in which daylight followed a broadly predictable daily cycle. By the 6th century, calendars had become sophisticated, and states could organise taxes, armies, markets, and religious observances, but no institution could restore normal sunlight if something high above the ground reduced how much solar energy reached the surface. This is where the event of 536 begins to feel different from an ordinary bad storm. A storm passes over a landscape and is usually recognised as weather. A distant atmospheric veil can be harder to understand, because the sky may look pale without revealing what created the change. There may be no nearby fire, no visible mountain erupting, and no obvious local cause. The disturbance can arrive from far beyond the horizon while appearing simply as weaker light. That mismatch between cause and experience matters. Humans are very good at learning from repeated local patterns, an ability that helped our ancestors survive changing environments for a very long time. But knowledge built from familiar patterns becomes less useful when the cause is rare, distant, and invisible. A farmer could know when to sow according to inherited practice, and still have no way to explain why the warmth of the season failed to arrive as expected. A chronicler could describe the sun and still have no way to know whether the same disturbance extended across seas and mountain ranges. Modern readers have the advantage of seeing evidence that those observers could not. Yet if we remain for a moment inside their limited view, the event begins not as a solved volcanic mystery, but as a simple and disturbing contradiction. Day had arrived, the sun was present, and still the familiar strength of daylight seemed to be missing. The sky had not disappeared, it had become unreliable. That difference mattered because a weakened sun offered no danger to confront, only altered conditions spreading silently across the landscape. The strange sky of 536 becomes more important when we look beyond a single writer or a single coastline. Evidence from different parts of the Northern Hemisphere suggests that the disturbance was not confined to one city or one political world, although the surviving records vary greatly in quality and detail. Some chronicles from regions farther east describe unusual atmospheric conditions, cold, or seasonal disruption during the middle of the 6th century. Other records are less precise, and their dates may not align perfectly with modern calendars. That uncertainty is important. Historical documents were not designed as climate instruments, and many were copied generations later. A phrase about mist, frost, failed crops, or a pale sun cannot automatically be treated as proof that every observer was describing the same process. What gives the year 536 its wider significance is not one dramatic sentence, but the way separate kinds of evidence begin to point toward a disturbance that reached far beyond the Mediterranean. In parts of Europe, later historical traditions preserve memories of hardship during this period. In regions of Asia, chronicles record abnormal weather and environmental stress around the same broad interval. Scholars compare these texts carefully because each one has its own context, language, and dating problems. The goal is not to make them identical. It is to ask whether their differences still fit a larger pattern. This way of thinking resembles something very old in human survival. Long before written history, people learned about landscapes by combining many small signals. A single cold day meant little. A change in animal movement, plant growth, rainfall, and temperature together could mean much more. Modern researchers do something similar with the 6th century, but across enormous distances and with records left by different societies. One clue alone is weak. Several independent clues that move in the same direction become harder to dismiss. Even then, geography matters. A broad atmospheric disturbance does not produce identical weather everywhere. Mountains, coastlines, latitude, prevailing winds, and local climate can change how a region experiences the same larger event. One community may face unusual cold, another may experience altered rainfall, a third may notice the sky but avoid severe harvest loss. This is why it would be misleading to imagine that the entire inhabited world suddenly entered one uniform season of darkness. The reality was more uneven, and that unevenness makes the story more scientifically credible, not less. Large environmental changes often move through local landscapes in different ways. What connects those places is not identical suffering, but evidence of a wider shift occurring within the same broad period. For the people living through it, however, there was no map showing that connection. A farmer in one valley could not know that distant forests were also growing poorly. A chronicler describing strange light had no way to compare notes with observers thousands of kilometers away. Each community lived inside a local fragment of something much larger. That limitation separates their experience from ours. Today, climate history can place distant records side by side and compare them with physical archives preserved in wood and ice. The 6th century observers had only memory, tradition, and what they could see around them. Their world was connected by trade, migration, religion, diplomacy, and war, but information still moved slowly. A strange season in one region might remain unknown elsewhere for months or years. This means that the full scale of the disturbance existed before any human being could understand its scale. That is one of the quietest but most important features of 536. The event was larger than the horizon of the people experiencing it. Their accounts remain fragmented because their lives were local, while the atmosphere above them was not. When those fragments are compared carefully, they begin to suggest that the weakened sunlight and abnormal seasons were not isolated curiosities, but parts of a wider environmental change whose boundaries no 6th century observer could see. The people who watched the weakened sun in 536 were not lacking intelligence. They were lacking a physical model of the atmosphere that would not exist for many centuries. A person could look upward and see that something had changed, but observation alone could not reveal what was happening high above the ground. The air around them appeared mostly empty. There was no way to measure tiny particles suspended at great altitude, no instrument capable of tracking changes in incoming solar energy, and no network connecting weather observations across continents. This created a strange situation in which the effects of a major environmental disturbance could be visible while its cause remained completely outside ordinary experience. Human beings had always survived by learning relationships between signs and consequences. Dark clouds might suggest rain. Frost could warn of danger to young plants. Changes in rivers, vegetation, or animal behavior could guide movement and seasonal decisions. These forms of environmental knowledge had deep roots in human history, because our ancestors depended on reading landscapes long before anyone kept written records. Knowledge accumulated because many natural processes repeated often enough to become familiar. The disturbance of 536 belonged to a different category. If the material reducing sunlight originated far away and travelled through the upper atmosphere, then the local sky offered almost no clue about where the disturbance had begun. There might be no nearby eruption to witness, no ash falling on a particular village, and no sound indicating that an event had occurred somewhere beyond the horizon. People experienced the consequence without experiencing the source. Written traditions could provide interpretations, but interpretations were shaped by the intellectual and religious worlds of their authors. Unusual celestial events could be understood as signs, warnings, or expressions of divine meaning. Such interpretations tell historians something important about the societies that recorded them, but they are not measurements of atmospheric chemistry. Modern readers must therefore keep two questions separate. What did people observe, and what caused what they observed? The first question can sometimes be approached through contemporary texts. The second requires evidence that those writers could never have collected. This difference is one reason the year 536 remained difficult to understand for so long. A description of a pale sun is striking, but by itself it cannot identify a volcano, determine the amount of material entering the atmosphere, or show how temperatures changed across different regions. Even several historical accounts cannot accomplish that alone. The missing information had been preserved somewhere else, not in books but inside natural archives. Trees growing through those years responded to temperature and moisture whether people understood the climate or not. Snow falling on distant ice sheets trapped chemical traces from the atmosphere without anyone knowing that those traces would survive for centuries. Lakes, glaciers, and sediments recorded environmental conditions in ways that no 6th century observer could read. In that sense, the Earth was keeping records at the same time that human chroniclers were writing their own. The two kinds of memory were very different. Human records preserved what seemed unusual, meaningful, or worth describing. Natural records preserved physical responses without explanation. Centuries later, those records could finally be compared. This is where the mystery of 536 begins to change. The strange sunlight no longer needs to stand alone as an isolated sentence from an ancient author. It can be tested against evidence that formed independently of human interpretation, yet even modern science must remain careful. Natural archives have uncertainties in dating. Local conditions influence how strongly a signal appears, and not every environmental change can be assigned to a single cause with complete confidence. The strength comes from agreement among different forms of evidence, rather than certainty from any one clue. For the people living in 536, none of that evidence was available. They saw the surface of the event while the mechanism remained hidden above them and its longer consequences were still unfolding. Their experience reminds us of an older limitation shared by every generation of humans. We can only interpret the world using the tools and knowledge available at the time. The sky had changed before anyone could understand why, and the explanation would remain buried in wood, ice, and atmosphere long after the witnesses themselves were gone. A tree does not remember a year in the way a person remembers one, yet its wood can preserve a physical record of the conditions under which it grew. In many temperate regions, trees add a new layer of growth during each growing season. Over time, those layers form rings that can be examined, measured, and compared. The width and structure of a ring are influenced by several factors, including the age of the tree, local soil, moisture, temperature, competition, and the length of the growing season. Because so many influences are involved, one narrow ring cannot simply be translated into one simple statement about climate. Researchers instead study patterns across many trees, often from the same region, and compare them with longer sequences built from living trees, archaeological wood, and preserved timber. When overlapping patterns match, scientists can place individual rings into a calendar sequence with remarkable precision. This method allows trees that died centuries ago to become part of a much longer environmental record. For the mystery of 536, that matters because trees were growing while human observers were looking at the strange sky. They responded to the same world but in a different language. A chronicler could describe weak sunlight. A tree could only grow according to the conditions available to it. If a summer was unusually cold, if sunlight was reduced, or if the growing season became shorter, growth could be affected, especially in places where temperature already limited how quickly wood formed. Yet even here, caution is necessary. Different species respond differently. A tree in a dry landscape may be more sensitive to moisture than temperature. A tree near the upper edge of a mountain forest may respond strongly to summer warmth. A forest growing in another region may show a weaker signal from the same broad climatic disturbance. Scientists therefore do not search for one magical ring that proves what happened across the world. They search for agreement among many records whose strengths and limitations are understood. This is one reason tree rings are so valuable for studying the 6th century. Human documents survive unevenly. Many ordinary people left no written account at all. Forests, however, continued to grow whether anyone recorded the weather or not. Their annual growth created a biological archive independent of political borders, languages, and historical memory. That archive also connects the story of 536 to a much older human dependence on seasonal biology. Long before written calendars existed, people watched plants because plant growth carried information about warmth, water, and the return of food. Agriculture made that connection even more direct. The same environmental conditions that influence forest growth could also influence fields and pastures, although crops and trees do not respond identically. When scientists examine ancient wood, they are therefore looking at one part of the environmental background within which human communities had to survive. The rings do not tell us what people felt. They do not reveal whether a family went hungry, whether a village migrated, or whether a ruler changed policy. Those questions require different evidence. What tree rings can do is help establish whether unusual growing conditions occurred, when they occurred, and how strongly they appeared in particular regions. In records from parts of the Northern Hemisphere, the middle of the 6th century contains unusually weak growth and signals consistent with severe summer cooling around the years associated with the atmospheric disturbance. Stable isotope measurements taken from some tree rings add another layer of information, because the chemistry of wood can reflect changes in environmental conditions during growth. None of this turns a tree into a perfect thermometer. It creates something more useful, an independent witness with known limitations. The people of 536 could see the sun, but could not measure the atmosphere. The trees could not see anything at all, yet their wood quietly preserved the biological consequences of the changing environment. Centuries later, those two forms of evidence could finally be placed beside one another. When researchers line up tree ring records from different regions of the Northern Hemisphere, the middle of the 6th century stands out in a way that is difficult to ignore. In several temperature-sensitive records, growth around 536 becomes unusually weak, suggesting that the growing season was colder or otherwise less favourable than normal. The exact response differs from forest to forest, because trees do not grow under identical conditions, but the broader pattern is consistent with a major climatic disturbance. Some records show very narrow rings. Others preserve changes in wood density or in the chemical composition of annual growth. Taken together, they indicate that the environmental shock was not merely a strange appearance in the sky. It reached living systems on the ground. For a tree growing near the climatic edge of survival, even a modest reduction in summer warmth can affect how much new wood is produced before cold weather returns. This sensitivity makes high-latitude and high-elevation trees especially useful for reconstructing past summer temperatures. When many such trees show reduced growth within the same narrow span of years, researchers have reason to look for a cause operating beyond one local valley. The evidence around 536 becomes even more important, because it appears near a moment already described in written accounts as a time of weakened sunlight. The agreement is not perfect, and it does not need to be. Historical texts describe what people noticed, while trees record biological response. One source can be incomplete and the other influenced by local climate, yet when independent records point toward the same broad interval, confidence grows that a real environmental disturbance occurred. Stable isotope studies add another layer. The ratios of certain forms of carbon and oxygen preserved in tree rings can reflect changes in sunlight, moisture, and growing conditions. In some 6th century records, these measurements support the picture of reduced solar radiation and cooler summers around the time of the 536 event. Scientists still have to interpret such signals carefully, because isotope values can respond to more than one environmental factor. Their value comes from comparison, not from treating a single measurement as a final answer. For human communities, the biological meaning of weak tree growth is indirect but important. A narrow ring does not prove that a nearby harvest failed, and a forest cannot tell us how much grain was stored in a town or how food prices changed. Trees and crops have different needs, and local agriculture may have been more or less resilient depending on rainfall, soil, crop choice, and access to trade. Still, forests reveal that the climate itself had changed enough to leave a measurable mark on living organisms. That matters because the human food system ultimately depended on the same seasonal energy. Since the first farming communities, people had relied on a recurring window of warmth and light in which plants could grow, mature, and be harvested. By the 6th century, states and markets had become more complicated, but they had not escaped that biological foundation. A cooler growing season could shorten the time available for crops to develop, though the effect would differ greatly by region and crop. The tree record cannot be converted directly into a map of hunger, but it can show that conditions controlling biological growth had shifted beyond ordinary local variation. The trees of 536 therefore preserve something larger than a cold summer in one place. They show that the disturbance reached into the annual growth cycle of forests across multiple regions, leaving a pattern that could survive long after written memories faded. This does not mean every landscape suffered equally, or that every year after 536 was uniformly cold. It means that the climate signal was broad enough to be visible in records separated by great distances. For modern science, that is a crucial step. The strange sun described by human witnesses begins to acquire a physical shadow in wood. The sky had changed, and now the forests were showing that the change had consequences. A single forest can tell us about a place. Several forests can begin to tell us about a much larger event. That is why the strongest tree ring evidence for the disturbance around 536 does not come from one famous tree or one unusually narrow ring. It comes from comparison. Researchers build long chronologies from many trees and examine whether unusual growth appears at roughly the same time in records created independently of one another. When temperature-sensitive trees in different regions show weak growth around the same year, the possibility of a purely local explanation becomes less convincing. Local drought, insects, soil conditions, or competition can damage one forest without affecting another far away. A broad pattern across distant records suggests that some wider influence may have reached many landscapes at once. The signal around 536 is important in that way. Reconstructions from several regions of the Northern Hemisphere indicate unusually cold growing conditions in the middle of the 6th century. Yet scientists do not expect every chronology to look identical. Trees in Scandinavia, the Alps, Siberia, or other northern environments respond to different combinations of temperature and moisture. Some records preserve a dramatic reduction in growth. Others show a weaker change. A missing signal in one place does not automatically contradict a strong signal elsewhere. Climate is spatially uneven. A broad atmospheric disturbance can alter average temperatures, while local winds, rainfall, elevation, coastlines, and soil conditions determine how strongly ecosystems respond. Recognizing that unevenness keeps the evidence from becoming a simplified story of a world experiencing exactly the same weather. Human beings have always lived inside such geographical differences. From the earliest dispersals of our species, survival depended on adjusting to local environments rather than inhabiting one uniform climate. By the 6th century, agriculture had made those local differences especially important. A shortened growing season could be serious in a northern region where crops already had limited time to mature, while another region might experience a different combination of temperature and rainfall. Tree rings cannot reconstruct every field, but they can reveal the climatic background against which those fields existed. Their greatest strength appears when they are compared with written observations. A chronicler described weakened sunlight. Distant trees recorded reduced growth. Neither source was created to confirm the other. One was produced by a human mind describing an unusual world. The other formed automatically as living tissue responded to environmental conditions. Agreement between such independent records is more persuasive than repetition within a single type of evidence. It also changes the meaning of the ancient descriptions. A pale sun no longer has to be treated only as unusual language preserved in an old manuscript. If biological archives formed during the same period show conditions consistent with cooling and reduced growth, the written testimony gains a physical context. The reverse is also true. Tree rings reveal environmental stress, but human accounts help show that people noticed abnormal conditions in the sky around the same historical moment. Neither can explain the entire event alone. That limitation prevents a common mistake in reconstructing the past, turning one clue into a complete story. Trees cannot identify what every community ate, how many people moved, or whether a political change had one environmental cause. Historical texts cannot measure temperature across continents. When different forms of evidence answer only the questions they can answer, the reconstruction becomes stronger. The picture emerging around 536 is not based on one dramatic discovery. It is built from convergence. Human memory preserved an abnormal sky. Forests preserved abnormal growth. Later evidence from another natural archive would preserve traces of material that had passed through the atmosphere. Together they begin to transform an ancient mystery into a testable environmental history, while leaving the central question unresolved. What could have changed the atmosphere strongly enough for people to notice the sun and for trees far apart to record the same troubled years? Far from the cities and farms of the 6th century, snow was falling on ice sheets that no human observer understood as archives. In places where annual snowfall can survive without fully melting, each new layer compresses the layers beneath it. Over long periods, snow becomes firm and then dense glacial ice. Trapped within that ice are tiny amounts of dust, sea salt, volcanic chemicals, and other material that once moved through the atmosphere. Modern researchers can drill deep cores through these frozen layers and study changes in their chemistry through time. In this way, an ice sheet becomes a record created without human writing. It does not preserve thoughts, fears, or explanations. It preserves traces of what passed through the air. This is especially useful for studying large volcanic eruptions because eruptions can release sulfur gases that are transformed in the atmosphere into sulfate aerosols. Some of that material eventually returns to the surface and can be deposited in snow. If a sufficiently large eruption sends sulfur high into the atmosphere, its chemical signal may later appear in ice cores taken far from the volcano itself. That does not mean every sulfate layer has a simple interpretation. Researchers must distinguish volcanic signals from other sources, build accurate timescales, and compare cores from different locations. The dating of ancient ice is itself a scientific task, and improvements in chronology can shift how particular layers are matched to historical years. This caution is essential for the events around 536, because a difference of even a year or two can change how a chemical layer is compared with written accounts or tree growth. Scientists therefore rely on several methods to strengthen the chronology, including counting annual layers where possible, and using known markers that can be recognized across different records. The result is not a perfectly labeled calendar trapped in ice, but a carefully constructed timeline with measurable uncertainties. What makes this natural archive so powerful is that it records a different dimension of the same environmental disturbance seen in trees. Tree rings mainly show how growing organisms responded to conditions at the surface. Ice can preserve material connected to what entered the atmosphere itself. The distinction brings us closer to the hidden mechanism behind the pale sun described in 536. Human witnesses saw altered daylight. Trees later revealed biological stress. Ice offers the possibility of finding a chemical fingerprint from the atmosphere above both of them. This connection also reaches back to the earliest relationship between humans and climate. Our ancestors could respond to cold, drought, or changing vegetation, but for most of human history, the chemistry of the atmosphere was invisible. People experienced climate through consequences on bodies, food, water, and landscapes. Only very recently have we learned to recover ancient atmospheric information from places where no one was present to record it. A layer of snow falling on Greenland or Antarctica in the 6th century had no meaning to anyone at the time. Yet that snow could receive particles transported over enormous distances and then seal them into ice. Century after century, additional snow buried the evidence deeper. Empires changed, languages disappeared, buildings collapsed, and manuscripts were copied or lost, while the chemical traces remained frozen in darkness. When scientists finally brought those cores to the surface, they gained access to a form of evidence entirely independent from 6th century storytelling. The ice still cannot tell us what one farmer experienced or how one community responded. It cannot identify every eruption by itself, but it can show that the atmosphere carried unusual amounts of volcanic material during a specific interval. For the mystery of 536, that capability matters because it turns an ancient description of dim sunlight into a question that can be tested chemically. The sky left a record, but it was stored where the people beneath it could never have known to look. In that sense, the ice preserved evidence from an atmosphere whose workings remained completely hidden to them. When scientists examine the ice that formed around the middle of the 6th century, one chemical signal becomes especially important: sulfate. Large volcanic eruptions can release sulfur gases high into the atmosphere, where chemical reactions transform part of that material into tiny sulfate-rich particles. Some remain aloft long enough to spread far from the source before eventually returning to the surface. In polar regions, falling snow can capture those particles and bury them inside annual layers of ice. Centuries later, a narrow rise in sulfate concentration can reveal that the atmosphere once carried an unusual volcanic burden. Around the years associated with the dimming described by 6th century observers, Greenland ice cores preserve such a signal. Improved ice core chronologies have strengthened the placement of major volcanic sulfate deposition near 536, and another major signal appears only a few years later, around 540. This does not mean that a layer of sulfate tells us everything we want to know. It does not automatically identify the volcano, determine exactly how dark the sky became in every region, or measure how each harvest was affected. Its importance is more fundamental. It shows that volcanic material entered the atmosphere at almost the same time that written sources describe weakened sunlight and tree rings record poor growing conditions. The ice therefore supplies evidence that neither a chronicler nor a forest could provide. A written account can tell us that the sun appeared dim. A tree can tell us that biological growth was disturbed. Sulfate in ice points toward a physical process capable of connecting those observations. The strength of that connection depends on dating, and dating ancient ice is not trivial. Snow accumulation varies from year to year. Layers can thin as they are buried. Chemical markers must be compared among different cores. Researchers have repeatedly refined ice core timescales so that volcanic layers can be matched more reliably with tree ring records and historical dates. These improvements are one reason modern reconstructions of 536 are stronger than older interpretations based mainly on written descriptions. The evidence has not become perfect. It has become more tightly synchronized. That distinction is important, because a scientific reconstruction gains reliability when several independent archives agree within the limits of their own uncertainty. The sulfur signal also helps explain why the event cannot be understood simply as local smoke or ordinary weather. Material capable of producing a detectable volcanic layer in distant polar ice had entered atmospheric circulation on a large scale. Yet even that statement needs restraint. The amount of sulfate deposited in one ice core is not a direct map of what every person breathed or saw, and scientists use models and multiple cores to estimate the broader atmospheric loading. For people living in 536, none of these processes were visible. They could see a pale sun and experience changing seasons, but the particles responsible for altering the passage of sunlight were too small and too high to be understood. This gap between human perception and atmospheric process reaches back through our species' entire history. Humans evolved to recognize nearby causes. Fire gives smoke, clouds bring rain, frost damages plants. A distant eruption whose sulfur reaches the upper atmosphere breaks that familiar connection. The source may be beyond the horizon while the consequence arrives overhead. By the 6th century, societies could move armies, collect taxes, construct monumental buildings, and maintain trade across seas. Yet they still had no way to observe the invisible chemistry above them. The ice cores reveal what their eyes could not. Around the time the sun seemed to lose its strength, the atmosphere carried a volcanic signature strong enough to become frozen into polar snow. Then, only a few years later, another major sulfate signal appeared. This is the point at which the year 536 begins to look less like an isolated mystery of ancient writing, and more like the opening of a sequence of environmental shocks, whose full scale was still waiting to be understood. The strongest case for a major environmental disturbance around 536 does not depend on one ancient sentence, one narrow tree ring, or one sulfate layer buried in polar ice. It depends on the way these records, created by completely different processes, begin to converge. Human writers described a sun that seemed unusually weak. Trees growing across parts of the northern hemisphere recorded poor growth and signals consistent with unusually cold summers. Ice cores preserve volcanic sulfate deposited close to the same period. Each archive has limitations. Written sources can be incomplete or difficult to date precisely. Tree growth responds to local conditions as well as regional climate. Ice core chronologies require careful synchronization, and sulfate alone cannot identify every eruption. Yet these weaknesses make agreement among independent records more important. If a chronicler had been the only witness to a dim sun, historians might wonder whether the description was exaggerated or metaphorical. If one forest alone showed weak growth, researchers might suspect drought, insects, or another local cause. Around the middle of the 6th century, however, those different lines of evidence overlap closely enough to support a broader conclusion. A substantial volcanic disturbance affected the atmosphere and was followed by significant cooling in parts of the northern hemisphere. This is not the same as saying that every place became equally cold or that every society experienced famine. The physical event was broad, while its human consequences were filtered through geography, crops, trade, wealth, political organization, and local weather. That distinction keeps the reconstruction grounded. It also shows why modern knowledge of 536 could never have come from historical texts alone. The people living through the event saw only fragments. A person under a pale sky could not see sulfur moving through the upper atmosphere. A farmer watching plants develop slowly could not know that distant trees were recording similar stress. Someone living near the Mediterranean had no access to snow falling on Greenland, where chemical traces were being preserved for future study. Human experience remained local, while the atmospheric disturbance crossed boundaries that no 6th century observer could measure. This gap between local perception and planetary process is deeply connected to the history of our species. Humans evolved by learning from immediate environments, where water returned, when plants ripened, which seasons brought animals, and how landscapes changed from year to year. Rare atmospheric events are different. Their causes can be separated from their effects by thousands of kilometers. The sky above one community may change because of an event no one there witnessed. In 536, that separation was almost impossible to overcome. Modern science reduces that distance by comparing archives that nature created independently. Wood records biological response, ice records atmospheric chemistry, historical writing records human observation. When these archives agree, they do not become one perfect story. They become a network of evidence in which each record answers a different question. The trees tell us that growing conditions changed. The ice tells us that volcanic material entered the atmosphere. The texts tell us that people noticed unusual daylight. Together, they make it difficult to explain the year as a local weather anomaly or a literary invention. Yet an important uncertainty remains. Evidence for volcanic activity does not automatically reveal which volcano produced the first major disturbance. Chemical traces can narrow possibilities, models can suggest likely regions, and volcanic deposits may eventually provide stronger matches, but the source associated with the 536 event has not been identified with complete confidence. That uncertainty is not a weakness. It is part of what makes the reconstruction scientifically honest. By the time the three archives are placed together, the central mystery has changed. The question is no longer whether something unusual happened. The evidence strongly supports that it did. The harder question is what kind of eruption could alter the atmosphere so widely, dim sunlight across distant regions, and leave its consequences recorded in human memory, living wood, and ancient ice. When people imagine a volcanic eruption darkening the sky, the first image is usually ash. Ash is visible, heavy compared with gas, and capable of covering nearby landscapes in grey material. Close to a volcano, ash can damage crops, contaminate water, collapse roofs, and make breathing difficult. Yet ash alone is not the best explanation for a dimming that affects regions far beyond the eruption itself for many months. Most volcanic ash falls out of the atmosphere relatively quickly, especially the larger particles. The more important agent in broad, longer-lasting volcanic cooling is often sulfur released as gas. During a sufficiently powerful eruption, sulfur dioxide can be injected high into the atmosphere. There it can undergo chemical reactions that produce tiny droplets and particles containing sulfuric acid and sulfate. These particles form an aerosol veil that is largely invisible to someone standing on the ground. Unlike the dark cloud of ash people may picture, such a veil can spread through the stratosphere and remain there long enough to influence how sunlight moves through the atmosphere. Some incoming solar radiation is scattered or reflected back towards space, so less energy reaches the surface. The result is not permanent darkness, and not the disappearance of the sun. It is a reduction in the amount of solar energy available to warm land and oceans. That distinction helps make sense of the 6th century accounts. A person could still see the sun while noticing that its light seemed weaker or strangely altered. The atmosphere did not need to become black. It only needed to change how light passed through it. The scale of the climatic response depends on many factors, including how much sulfur reaches the stratosphere, the height of injection, the latitude of the eruption, atmospheric circulation, the season, and interactions within the climate system. For that reason, scientists cannot look at a sulfate layer and translate it into one exact temperature for every place. Volcanic cooling is uneven. Some regions may cool strongly in a particular season, while others experience smaller temperature changes or shifts in rainfall. Oceans, winds, and land surfaces redistribute energy, creating regional patterns that differ from the global or hemispheric average. This is another reason the year 536 should not be described as a world placed under one identical blanket of cold. The physical mechanism may be widespread while the local consequences remain diverse. For human beings, however, even a temporary reduction in summer warmth can matter because our food systems have always depended on solar energy entering biological systems. Long before farming, human populations followed landscapes shaped by sunlight, temperature, water, and plant growth. After agriculture became widespread, the connection became more concentrated. Fields had to pass through a sequence of growth before harvest. Pasture had to support animals. Fruit, grain, and other crops required conditions suited to their development. A change high in the atmosphere could therefore move downward through a chain that no 6th century observer could see. Sulfur altered atmospheric transparency, reduced incoming energy, affected seasonal temperatures, changed plant growth, and eventually placed pressure on human food supplies. Not every link was equally strong in every location, and no single eruption automatically caused famine everywhere. Local rainfall, crop choice, storage, trade, and wealth still mattered, but the mechanism explains how an event at one point on Earth could influence people who never saw the volcano and never experienced falling ash. This is the central difference between ash and aerosol. Ash announces an eruption locally. Sulfate aerosols can carry its climatic influence far beyond the horizon. They can remain high above ordinary weather systems, spreading through atmospheric circulation while people below continue their daily lives without knowing what has entered the sky. By the time crops respond or summer temperatures weaken, the original eruption may already be distant in both space and time. For the people of 536, the visible mystery was a pale sun. For modern science, the more important clue is the invisible veil that could stand between that sun and the ground. Once sulfate aerosols are spread through the stratosphere, the climatic effect does not remain above the place where the eruption occurred. The atmosphere moves continuously, carrying fine particles across large distances while the Earth below continues to receive slightly less solar energy than it otherwise would. That change may sound small when described only as a reduction in incoming sunlight, but climate depends on the balance between energy arriving from the sun and energy leaving the Earth. If a volcanic aerosol layer reflects or scatters part of the incoming radiation, the surface can cool until the atmosphere gradually clears. The most important effects are often seen during the growing season, when even a relatively brief period of unusual cold can influence plants, soils, snow cover, and the timing of seasonal development. This is one reason the middle of the 6th century appears so strongly in tree ring records from temperature-sensitive regions. The forests were not recording the eruption itself. They were recording the altered conditions that followed from changes in the atmosphere. The same physical process helps explain how communities separated by seas and mountain ranges could experience related environmental stress without ever knowing they were connected. A person living near the Mediterranean did not need to see a volcano for the atmosphere above that person to carry material produced by an eruption elsewhere. A farmer in northern Europe could experience an unusually cool summer even if no ash had fallen nearby. The distance between the source and the consequence is what makes large volcanic events so different from most hazards familiar to human beings. Fire usually burns near its source. Flooding follows water through a landscape. Volcanic climate effects can travel through a layer of the atmosphere that people on the ground cannot see or reach. Yet the cooling itself is not uniform. The same aerosol veil can interact with winds, oceans, sea ice, rainfall patterns, and regional geography in different ways. Some areas may experience strong summer cooling. Others may see smaller temperature changes but unusual precipitation. Coastal regions may respond differently from continental interiors. Mountain environments may preserve a clearer temperature signal than lowlands. This is why scientists reconstruct the event using networks of evidence rather than assuming that one record represents the whole northern hemisphere. It also helps explain why human consequences cannot be calculated directly from a single estimate of temperature change. A cooler summer could shorten the growing season, but the result for food production would depend on what was planted, when it was planted, how much rain fell, and whether stored supplies or imported food were available. One community might face serious shortages while another nearby community remained comparatively stable. The atmosphere could create a broad climatic pressure without producing one identical human outcome. That pattern reaches back to the deepest history of our species. Humans survived past climatic shifts not because every population experienced them in the same way, but because local landscapes offered different risks and opportunities. Movement, exchange, diverse diets, and cooperation allowed some groups to adjust when conditions changed. Farming later increased food production and supported larger populations, but it also placed many communities within narrower seasonal schedules. Seeds had to germinate, crops had to mature, and harvests had to arrive before cold or excessive rain damaged them. A volcanic disturbance high above the Earth could interfere with that schedule without touching a field directly. The connection ran from invisible particles in the stratosphere to altered sunlight, from altered sunlight to temperature, from temperature to biological growth, and from biological growth into the human systems built around food. Modern climate science can describe that chain because we can study eruptions whose atmospheric effects have been observed directly and compare those mechanisms with ancient records. For 536, the evidence supports a major volcanic influence on climate, but it does not allow us to reconstruct one exact weather sequence for every settlement. That uncertainty matters. It prevents a scientifically supported mechanism from becoming an exaggerated story of universal darkness or universal famine. What can be said more securely is that a volcanic disturbance had the capacity to change the energy reaching the surface across wide regions, and that natural archives record severe cooling around the same historical interval. The people living beneath the altered sky could only experience the local result. They had no way to know that the strange summer outside their homes might be connected to atmospheric changes extending far beyond anything they could see. Knowing that volcanic aerosols can cool distant regions does not solve the geographical mystery. The ice tells us that volcanic material entered the atmosphere around the time the sun dimmed, and the trees tell us that growing conditions deteriorated across parts of the northern hemisphere, but neither record automatically gives us the name of the volcano that began the disturbance. Scientists have proposed several possible sources, yet the first major eruption associated with 536 has not been tied to one volcano with complete confidence. Identifying an ancient eruption requires more than finding a large volcano that was active at roughly the right time. Researchers look for evidence connecting the eruption to material preserved elsewhere. Volcanic ash contains tiny fragments of glass whose chemical composition can sometimes be compared with deposits from known volcanoes. If microscopic particles in an ice core match material from a particular eruption, and the dates also agree, the case becomes stronger. But ancient deposits are incomplete. Some eruptions occurred in remote regions, some ash layers were eroded or buried. Some eruptions produced widespread sulfur without leaving easily identified ash at distant locations. The atmosphere can transport gases and fine particles in ways that make the source difficult to trace centuries later. This is why it is safer to speak of a major volcanic event than to attach a famous mountain to 536 as if the matter were settled. The broader conclusion does not require certainty about the volcano's name. A major injection of volcanic sulfur is strongly supported by the ice core record, while tree rings and historical observations show environmental changes that fit the expected consequences of such an event. The uncertainty lies mainly in the precise source and details of the eruption, not in the existence of a major atmospheric disturbance. Human beings naturally prefer a single object that can carry the story: one volcano, one date, one cause. Ancient environmental history is often less tidy. Evidence may establish the mechanism before it identifies the location. It may reveal the timing before it reveals the source. This reverses the way a 6th century witness experienced the event. People living then knew where they were but did not know what had happened in the atmosphere. Modern researchers can describe much of what happened in the atmosphere while still being uncertain about exactly where the first eruption occurred. Between those perspectives lie centuries of evidence preserved in wood, ice, sediment, and written memory. The uncertainty also protects us from a misleading picture of causation. Even if one volcano were identified with great confidence, that would not mean every hardship of the 6th century could be traced directly to that mountain. Local weather, political conflict, trade, land use, disease, and social inequality all shape what happens after an environmental shock. A volcanic eruption can create broad pressure without writing the same history for every society beneath its influence. This resembles the much older history of human adaptation. Our ancestors faced droughts, cold periods, changing coastlines, and shifting ecosystems, but environmental change never produced one automatic human response. People adjusted through movement, cooperation, technology, exchange, and sometimes conflict. By 536, those responses existed within larger and more settled societies, where resilience and vulnerability had become more complicated. The missing name of the volcano, therefore, does not weaken the central evidence. It reminds us that scientific confidence has levels. We can be highly confident that large volcanic eruptions disturbed climate in the middle of the 6th century while remaining less certain about the source of the first event. We can recognize that the strange sunlight described by witnesses fits a volcanic aerosol veil without pretending that every surviving sentence is a direct measurement. We can follow the climatic signal into trees and ice without converting it into a universal story of famine. What remains unresolved is where the first powerful pulse began and how its effects differed from one region to another. That uncertainty matters because the disturbance of 536 was not the only major volcanic shock waiting for the people of the 6th century. The first climatic blow of the middle 6th century did not need to destroy a city in a fear, single day to become dangerous. Its power came from duration, timing, and the way ordinary systems of survival depended on a predictable growing season. After the atmospheric disturbance around 536, tree ring records from several parts of the northern hemisphere indicate unusually cold summer conditions. Historical descriptions of weakened sunlight fit the same broad interval. For farming communities, the problem was not simply that the sky looked strange. Less favourable warmth during the months when crops needed to develop could shorten the effective growing season and slow biological growth. The result would not have been identical everywhere. Different crops respond differently to cold, and rainfall, soil, altitude, and local farming practices could either soften or deepen the effects. Some communities may have experienced serious harvest difficulties, while others may have been protected by local conditions or access to stored food. This unevenness matters because the year 536 is often described as if one disaster fell equally on every person alive. The evidence supports a broad climatic shock, but not one universal human experience. Even so, repeated cold conditions could reduce the margin of safety on which many households depended. A family did not need to lose an entire harvest for life to become harder. A smaller yield could mean less grain stored for winter, fewer reserves for the following spring, and less fodder for animals. If prices rose in markets, poorer households could feel pressure before wealthier ones. If livestock had less pasture or stored feed, people might have to choose between preserving animals and consuming resources needed later. These decisions were part of a chain connecting atmosphere to biology and biology to society. The chain was ancient. Long before agriculture, human populations survived environmental change through mobility, broad diets, shared knowledge, and cooperation. Farming created new forms of security by producing storable food, but it also tied communities more closely to seasonal schedules and particular landscapes. By the 6th century, large political systems could collect grain, move supplies, and support cities. Yet those systems could not create a harvest that climate had prevented from growing. Their resilience depended on surplus, and surplus depended partly on previous good years. This is why the first shock of 536 should be understood not only as an episode of cooling, but as a test of accumulated buffers. Stored grain, trade routes, household wealth, livestock, and social obligations could all absorb some pressure. But every reserve that was used in one difficult season was no longer available for the next. A community that entered 536 with strong stores and functioning exchange networks might cope far better than one already weakened by war, taxation, local crop problems, or poverty. The climate did not erase those differences. It interacted with them, nor should poor tree growth be translated automatically into famine. Forests are climate indicators, not census records. Historical sources from the period are incomplete, and they do not allow us to calculate one reliable death toll from the first climatic shock. What they do allow, when combined with natural archives, is a more careful conclusion. The atmosphere changed enough to reduce summer warmth across wide regions, and biological systems recorded the stress. Human societies then had to absorb that stress using whatever reserves and institutions they already possessed. For people living through those seasons, the crisis would have unfolded gradually. There was no clear moment when everyone could say that an extraordinary climatic episode had begun. There were only cooler days, weaker growth, uncertain harvests, and stores that might not last as comfortably as expected. The danger of 536 was therefore not only what happened in that year, it was what the first shock removed from the years that followed: surplus, confidence, and the ability to recover quickly if the climate turned against them again. That possibility would soon become more important than anyone in 536 could have known. 63,827. The climate shock that began around 536 did not stand alone for long. Only a few years later, ice core records preserve another large volcanic sulfate signal, associated with an eruption around 540. Tree ring evidence also points to renewed or continuing severe summer cooling during this interval. For communities that had already spent several seasons adjusting to unusual conditions, this second disturbance mattered for a simple reason. Recovery requires time. A difficult harvest can sometimes be survived with stored grain, livestock, trade, assistance from relatives, or supplies moved from regions with better production. But these protections depend on reserves that must eventually be rebuilt. If another climatic shock arrives before that rebuilding is complete, the same society can face the new disturbance with fewer options than it had before the first one. This is why the events around 536 and 540 are often considered together as a volcanic double event, while still being recognized as separate eruptions. They did not create one continuous cloud from a single source. Rather, they place strong volcanic forcing into the climate system twice within a relatively short interval. The exact climatic response varied across regions, but natural records show that the middle of the 6th century contained some exceptionally cold summers in parts of the northern hemisphere. The significance lies not only in how cold one year may have been, but in the interruption of recovery. Imagine a farming household that had already drawn down part of its grain reserve after a weak harvest. Seeds still had to be saved for planting. Animals still needed winter fodder. Tools had to be maintained. Taxes or obligations might still be due, and food could not simply be consumed without regard for the following season. If conditions improved, these pressures could gradually ease. Another major volcanic disturbance could delay that process. A society does not need to collapse for such cumulative stress to matter. Households may sell animals, consume food intended for later use, reduce exchange, postpone construction, or depend more heavily on relatives and local authorities. We cannot assume that every community made those choices, because the historical evidence rarely preserves decisions at that level. What matters is the underlying principle. Repeated environmental shocks reduce the time available for biological and social systems to return to their previous state. This pattern has deep roots in human history. Our species evolved under changing climates, and flexibility was one of the qualities that allowed human populations to occupy environments ranging from tropical landscapes to cold northern regions. But flexibility does not mean unlimited resilience. Movement, dietary diversity, cooperation, and exchange work best when alternative resources remain available. Agricultural societies develop different buffers, including stored harvests, livestock, trade routes, and political redistribution. Each buffer could absorb pressure, but none was infinite. A second major cooling episode could therefore affect populations differently depending on how much of those buffers remained. The climatic evidence also warns against treating 536 as a single isolated year whose danger ended when the calendar changed. Volcanic aerosols eventually leave the stratosphere, but the human consequences of a poor growing season can persist after the atmosphere begins to clear. Seed stocks, animal numbers, household wealth, and stored food carry conditions from one year into another. When a later eruption introduces renewed cooling, it enters a world already shaped by what came before. In some places, that may have meant severe agricultural strain. In others, the effects may have been smaller because local rainfall, crop choices, trade, or political organization provided protection. Scientists cannot reconstruct one universal outcome, and it would be misleading to describe every inhabitant of Eurasia as living through the same famine. Yet the physical sequence itself is increasingly clear. Ice cores record major volcanic sulfur associated with both 536 and 540, while tree ring reconstructions show pronounced cooling around the same period. Later research has also identified another eruption in the 540s, smaller than the two major events but potentially relevant to the persistence of cooler conditions. What had begun as a strange dimming of sunlight was therefore becoming something larger than a single bad summer. The first atmospheric shock had tested the reserves of human communities. Before the climatic system and the societies beneath it had fully returned to ordinary conditions, another powerful eruption added new pressure. The people who experienced these years could not know that they were living through a sequence. They could only notice that the familiar rhythm of recovery was taking longer than expected. The climatic disturbance that began in the middle of the 6th century did not end when the first aerosol veil faded from the atmosphere. A sequence of major volcanic eruptions, including the events associated with 536 and around 540, was followed by decades in which regions of the Northern Hemisphere experienced unusually cool conditions. Researchers have used the term Late Antique Little Ice Age for a period of persistent cooling beginning in the 6th century, although the exact timing, geographical extent, and strength of that cooling vary among reconstructions. The name should therefore be used carefully. It does not mean that every region of the world became continuously cold or that every year was worse than the one before it. Climate still fluctuated from season to season and from place to place. What the evidence suggests is that repeated volcanic forcing helped push regions of the Northern Hemisphere into a cooler background state that lasted far longer than the immediate atmospheric lifetime of one eruption. This can happen because the climate system has memory. Aerosols themselves eventually disappear, but oceans, sea ice, snow cover, and atmospheric circulation can respond more slowly. Several strong eruptions occurring close together can reinforce cooling before the system has fully recovered from the previous disturbance. Tree ring reconstructions show that some of the coldest northern summers of the past 2 millennia occurred during the middle 6th century, while ice cores reveal the volcanic sequence that helped drive those changes. Yet the connection between climate and history must still be handled with restraint. A cooler climatic period does not automatically explain the fall of a kingdom, the movement of a population, or the outcome of a war. Human societies respond through institutions, trade, technology, migration, cooperation, conflict, and choices that cannot be reduced to temperature alone. The significance of prolonged cooling is that it changes the background against which those choices are made. A community facing one poor harvest might rebuild its stores during the next several good years. If favorable years become less reliable, recovery becomes harder. Livestock numbers may take time to recover. Seed reserves can be reduced. Wealth lost during shortage may not return quickly. Networks of exchange can help, but they are most effective when other regions still have surplus to share. This is where the 6th century experience connects again with the much older history of humanity. Our species survived repeated environmental changes because people could adjust behavior across generations. But every adaptation depends on available alternatives. A colder landscape may favor one crop over another, one route over another, or one settlement pattern over another. Those changes unfold gradually, often without anyone recognizing that they are living through a distinct climatic era. The people who survived the years after 536 did not know that future researchers would group decades of their lifetime into a named period of cooling. They experienced individual winters, summers, harvests, illnesses, journeys, and political events. The long pattern becomes visible only when centuries of natural evidence are assembled afterward. That difference between lived time and reconstructed time is important. It prevents us from imagining that everyone in the 6th century understood themselves to be inside one continuous catastrophe. Many years would still contain ordinary work, successful harvests, births, trade, and recovery. Some regions may have been affected only modestly, others face stronger stress. The climatic background increased risk, without determining every outcome. In this sense, 536 was not simply a terrible year followed by a return to normal. It marked the beginning of a sequence in which repeated eruptions and climatic responses extended the disturbance beyond a single season. The pale sun was temporary, but the environmental consequences could last much longer. What had first appeared as an unusual sky was becoming part of a colder historical landscape in which human resilience would be tested not only by one shock, but by the length of time required for stability to return. A colder summer does not harm human beings first by touching the body directly. It begins lower in the chain of life, with plants. Every field depends on a limited window of light, warmth, water, and time. Crops must germinate, produce leaves, build tissue, flower, and mature before conditions become unfavorable. When a volcanic aerosol veil reduces the amount of solar energy reaching the surface and lowers summer temperatures, that biological schedule can be disturbed. The effect is not simply that plants receive less light. Cooler soils can delay germination, lower temperatures can slow growth. A shorter warm season can leave grain or other crops with less time to mature before autumn cold arrives. In some regions, excessive rain or altered circulation may add further stress, while in others moisture conditions may remain suitable. The outcome therefore depends on crop, location, weather, and farming practice. There is no scientific basis for imagining that every field in 536 failed in the same way. What the climatic evidence does support is that many northern regions experience conditions capable of reducing biological productivity during crucial months. This matters because agriculture is an organized way of capturing solar energy. A grain field takes energy that arrives from the sun and stores part of it in plant tissue that humans can harvest, process, and eat. Animals grazing on pasture depend on a similar pathway. When climate changes the rate at which plants grow, the disturbance can move upward through the food system even if no person understands the atmospheric cause. That relationship is far older than farming. The first members of our species survived by following environments whose plants and animals were themselves governed by seasonal energy. Human mobility once offered more flexibility when one local source of food weakened, although movement was never an effortless solution. Agriculture later allowed communities to produce and store larger quantities of food in one place, supporting denser settlements and more specialized societies. The advantage came with a new sensitivity. A large population tied to fields cannot simply move whenever a growing season becomes unfavorable. By the 6th century, that dependence had been woven into taxes, rents, markets, armies, religious institutions, and urban supply systems. A field was no longer only a source of food for the household beside it. Its harvest might also support people who never touched the soil. This is why reduced plant growth can become a social problem without requiring total crop failure. A modest decline in yield, repeated across many farms, can leave less grain for storage, less fodder for animals, and less surplus for exchange. A household may still eat, but its margin for the following winter becomes narrower. A town may still receive grain, but prices may become harder for poorer people to bear. An estate may still meet its obligations, but only by drawing more heavily on reserves. None of these outcomes can be assigned automatically to every region after 536, because surviving records are too uneven to support that level of detail. The biological mechanism, however, is straightforward. Plants convert environmental conditions into growth, and human societies convert plant growth into food, wealth, labor, and security. When the growing season becomes colder or shorter, pressure enters that chain at its base. The same principle would have been familiar in practical form to farmers, even if its atmospheric cause was invisible. They could see whether seedlings emerged slowly, whether grain ripened late, or whether pasture was poor. They did not need a theory of volcanic aerosols to recognize that the land was producing differently. What they could not know was that forests across distant regions were also recording weak growth, or that sulfur preserved in polar ice would later reveal an atmospheric disturbance occurring at the same time. The human story of 536, therefore, begins to move from the sky into the soil. The pale sun was not dangerous merely because it looked strange. Its deeper importance was that solar energy stands at the beginning of nearly every food chain on which human life depends. When that energy was altered during already short northern growing seasons, the consequences could travel quietly, from leaf to seed, from pasture to animal, and from harvest to the bodies waiting for food. One weak harvest can be painful without becoming catastrophic. The deeper danger begins when another difficult season arrives before households have rebuilt what they used to survive the first. Agricultural communities do not consume only what grows during the current year. They depend on food carried forward through time. Grain may be stored for winter, reserved for seed, exchanged for other goods, used to feed workers or animals, or kept as protection against an uncertain future. When yields decline, these different needs begin to compete with one another. Eating more of the stored grain may solve an immediate shortage while leaving less for planting. Preserving seed may protect the next harvest, while forcing a household to reduce consumption. Keeping livestock alive may require fodder that has also become scarce. Selling animals or possessions can provide temporary relief, but it may reduce the household's ability to recover later. None of these choices automatically describes every family living after 536, yet they show why repeated agricultural stress can become more serious than a single disappointing summer. Food security has a memory. What survives one year determines what is available when the next begins. This principle reaches back to the earliest farming communities, when humans first became increasingly dependent on crops that had to be planted months before they could be eaten. Storage changed human history because it allowed people to move calories across seasons. A harvest could support life long after the plants themselves had died. But storage also created a finite reserve that could be drawn down. By the 6th century, the same basic biological problem existed inside far more complicated societies. Villages produced food for themselves, but harvests could also support landlords, markets, armies, officials, monasteries, and towns. Trade allowed surplus from one area to compensate for shortage elsewhere, yet trade could not create grain where broad climatic conditions had reduced production across many supplying regions at once. The farther pressure spread, the harder it could become to find an unaffected source of surplus. Even then, scarcity would not have been equal. Wealthier households might purchase food for longer. Political authorities might redirect supplies towards cities or strategic populations. Rural families could have access to livestock, gardens, gathered foods, or local networks unavailable to urban residents. Coastal communities might receive imports that inland settlements could not. These differences remind us that climate creates pressure, while social organization determines much of how that pressure is distributed. A sequence of weak harvests can also change the meaning of an apparently normal year. Suppose one growing season produces enough food to avoid immediate crisis, but not enough to rebuild reserves depleted earlier. On the surface, conditions may look improved. Beneath that improvement, resilience remains lower than before. Another cold or wet season can then produce consequences more severe than the same weather would have caused several years earlier. This is why the events beginning in 536 cannot be understood only by asking whether one particular harvest failed. The more important question is whether communities had enough time and surplus to recover between shocks. The volcanic disturbances of the middle 6th century reduced that recovery time. Evidence does not allow us to trace a single chain of shortages across every region, and claims of universal famine would go beyond what the surviving record can support. What can be understood more securely is the mechanism of accumulation. Cooler growing conditions can reduce plant productivity, lower yields can reduce storage, smaller reserves can narrow choices during the following season. If another unfavourable year arrives, households and institutions may enter it with fewer buffers. Over several seasons, pressure can therefore build quietly rather than appearing as one sudden collapse. For the people living through these years, the most difficult feature may have been that no harvest existed alone. Every autumn carried the memory of the one before it, and every decision about what to eat, save, plant, trade, or feed to animals reached forward into a future whose climate had become less dependable. When food becomes less reliable, the human body does not immediately cross a simple line from health into starvation. The effects can appear gradually, beginning with smaller meals, less varied diets, and the replacement of preferred foods with whatever remains available. A household that still has enough calories to survive may nevertheless lose access to meat, dairy products, legumes, vegetables, or other foods that normally provide important nutrients. Adults may reduce their own intake to protect children or preserve stores, although surviving sources rarely allow us to know how individual 6th century families divided food during difficult years. What can be said more generally is that prolonged food insecurity places biological strain on the body. When energy intake remains below what daily work requires, stored energy is gradually used. Physical strength and endurance can decline. Maintaining body temperature in cold conditions may become more demanding. Recovery from injury or illness can become harder when nutrition is poor. Deficiencies in particular nutrients can create additional problems. Although the exact diets and nutritional status of communities after 536 cannot be reconstructed with enough precision to diagnose populations from climate records alone, this distinction is essential. A cold summer does not directly prove malnutrition, and a narrow tree ring cannot tell us what a person ate. The evidence instead reveals a chain of increasing risk. Climatic disturbance can weaken plant growth. Poorer harvests can reduce available food and reserves. Repeated shortages can make diets less secure. Biological stress then depends on how severe the shortage is, how long it lasts, and which resources remain accessible. Age, workload, illness, wealth, and social support can all influence how strongly an individual is affected. This basic vulnerability is ancient. For most of human existence, survival depended on obtaining enough energy from landscapes whose productivity changed with climate and season. Human beings evolved remarkable flexibility in diet and behavior, but our bodies never became independent of nutrition. Farming transformed how energy was gathered by concentrating it into cultivated fields and stored harvests. It allowed populations to grow and settlements to become more permanent, yet it also meant that failure in a limited number of important crops could place many people under pressure at the same time. By the 6th century, this biological dependence existed beneath layers of political and economic complexity. A city might receive grain through taxation or trade. A wealthy household might purchase food from farther away. A village might rely on livestock, gardens, stored grain, and help from neighbouring families. These arrangements could protect people, but they also determined who encountered scarcity first. Food insecurity is therefore never only a question of how much food exists across an entire region. Distribution matters, access matters, the ability to preserve seed and livestock while still feeding people matters. A society may possess grain somewhere while individual households remain unable to obtain enough of it. This is one reason it would be misleading to convert the climatic shock of 536 into a single mortality figure. Historical records are incomplete, archaeological evidence differs greatly by region, and many other forces shaped human health. Disease existed before the volcanic events. Warfare, displacement, sanitation, local harvest conditions, and ordinary inequalities also influenced survival. Climate could increase pressure without becoming the sole explanation for every death that followed. The most defensible conclusion is therefore quieter but more important. Repeated environmental stress can reduce the biological margin within which people live. A population does not have to be starving everywhere for weaker harvests to matter. Fewer calories, poorer dietary diversity, greater physical demands, and reduced reserves can leave some individuals less able to absorb additional shocks. The human body becomes the final destination of a chain that began far above it. Sulfur entered the atmosphere, sunlight was altered, summers cooled, plants grew differently, harvests became less dependable, and stored food could diminish. At every stage, geography and human choices changed the outcome. By the time the effects reached the body, the original eruption might be invisible and forgotten, yet the biological consequences of an uncertain food supply could still remain. Northern Europe faced the climatic disturbance of the middle 6th century, from a different starting point than warmer regions farther south. In Scandinavia and neighbouring northern lands, farming already operated within relatively short growing seasons, where the timing of spring warmth and summer temperatures could strongly influence whether crops matured before autumn cold returned. That does not mean northern societies were helpless. Communities had generations of experience with variable weather, livestock, storage, fishing, hunting, exchange, and the use of different landscapes. Yet resilience is never the same as immunity. When summer cooling becomes unusually strong, a system adapted to a narrow seasonal window can lose some of the time on which it depends. Tree ring records from northern Europe and Fennoscandia show that the middle 6th century included exceptionally poor growth in temperature-sensitive trees, consistent with severe summer cooling, following major volcanic eruptions. These trees were not growing in cultivated fields, so they cannot tell us directly how much grain was harvested. Their value is different. They show that the environmental conditions surrounding northern communities were unusually harsh at precisely the time when historical and ice core evidence indicate atmospheric disruption. In northern agriculture, a delayed spring or cool summer can influence several stages of production at once. Soil may warm more slowly, planting opportunities may shift, pasture growth may weaken, and grain may require longer to ripen. If cold arrives before crops have completed development, the amount or quality of usable harvest can decline, but local geography remains important. Coastal zones, inland valleys, uplands, and sheltered lowlands can experience the same broad climatic event differently. One settlement may have access to productive pasture or fishing grounds, while another relies more heavily on grain. One community may preserve larger stores or maintain stronger exchange networks. This is why archaeological evidence from Scandinavia must be read carefully. Changes in settlement, wealth, land use, or ritual behavior during the 6th century have sometimes been connected to the climatic crisis, and there are good reasons to investigate those connections. But climate should not be treated as an automatic explanation for every social transformation. Political competition, migration, inheritance, warfare, changing trade networks, and local decisions were also present. The environmental shock created pressure. People still determined how that pressure entered history. This distinction becomes clearer when we look at the deeper human relationship with northern environments. Long before permanent farming reached these latitudes, human groups survived there by adjusting movement, diet, technology, and seasonal behavior to landscapes where warmth was already limited. Agriculture did not erase that flexibility, but it changed the balance. Fields, livestock, stored fodder, houses, and established territories made communities more invested in specific places. A poor summer could therefore threaten not only the food growing that year, but also resources meant to carry animals and people through winter. If several difficult seasons arrived close together, rebuilding those resources would become increasingly important. Archaeology can sometimes reveal broad shifts in settlement or material culture after this period, yet translating those changes into exact population losses is difficult. Sites disappear for many reasons. Burial customs change. Buildings are abandoned and rebuilt elsewhere. The absence of material in one location does not automatically prove that everyone living there died. The strongest interpretation is therefore one that combines climate evidence with social evidence without forcing them into a single dramatic story. Scandinavia appears to have been especially exposed because cold season limits were already close to the threshold of successful cultivation in some areas, while the volcanic shocks of the 530s and 540s pushed summer conditions sharply downward. Some communities may have suffered severe shortages. Others probably found ways to buffer the disturbance through livestock, marine resources, stored food, exchange, or relocation. What matters is that the same atmospheric event encountered a northern world with its own ecological limits and its own forms of resilience. The year 536 was not one human experience repeated across a map. In Scandinavia, its meaning was shaped by short summers, local food systems, and the difficult question of how much environmental stress a community could absorb before adaptation became unavoidable. The Mediterranean world entered the climatic disturbances of the 6th century, with advantages that northern, farming regions did not possess. Growing seasons were generally longer, many landscapes supported crops adapted to warmer conditions, and the Roman and post-Roman economies connected farms, ports, towns, estates, and cities through networks of exchange. Grain, wine, olive oil, animals, and other goods could move over considerable distances. In principle, these connections gave communities ways to respond when one district produced less than expected. A poor local harvest did not always mean that a city immediately ran out of food. Supplies could sometimes arrive from another region, private merchants could redirect trade, and governments could use taxation or distribution systems to support selected populations. Yet the same complexity created another kind of vulnerability. Cities contained many people who did not grow their own food. Armies, administrators, artisans, religious institutions, and urban households depended on agricultural production occurring elsewhere, and on the ability of transport and markets to keep that production moving. Climate pressure could therefore travel through economic networks as well as through fields. A colder or unusually wet season in one supplying region might reduce output there, while disruption across several important producing areas could make replacement supplies harder to find. Even where enough food existed in aggregate, prices and access could change who was protected and who became exposed. Wealthier households could often withstand higher costs longer than poorer ones. Landowners with storage might have options unavailable to wage labourers or urban families buying food regularly. Political authorities might prioritize capitals, armies, or strategically important cities, leaving other communities to depend more heavily on local resources. These possibilities do not prove that one pattern occurred everywhere after 536. They show why the Mediterranean cannot be understood simply by asking whether its temperatures fell as sharply as those of northern Europe. Human vulnerability is shaped by institutions as much as by climate. This has a much deeper history. From the first agricultural settlements onward, humans gradually built systems that separated food production from food consumption. Storage allowed one season to support another. Trade allowed one landscape to support people living somewhere else. Political organization extended that separation further by collecting, transporting, and redistributing agricultural surplus. By the 6th century, some Mediterranean cities depended on networks far larger than any single community could personally observe. That complexity increased resilience when networks functioned well, because shortage in one place could be compensated by abundance in another. But resilience built on connection also depends on those connections continuing to work. Ships still had to sail, roads still had to be usable, merchants still had to trade, officials still had to organize supplies, and producing regions still had to generate enough surplus to export. Climate alone could not determine whether these systems succeeded. War, taxation, political decisions, piracy, local unrest, and ordinary commercial conditions also mattered. This is why it would be misleading to treat the climatic shock of 536 as a direct explanation for every economic or political difficulty in the Mediterranean. The more careful interpretation is that environmental stress altered the conditions within which those systems operated. If harvests weakened, less surplus might be available. If several seasons were poor, reserves could narrow. If prices rose, the burden could fall unevenly. If a region remained productive, trade could soften the shock elsewhere. In that sense, the Mediterranean response may have depended less on a single threshold of cold and more on the ability of social networks to redistribute risk. The written accounts of strange sunlight from this broader world are valuable precisely because they record what people noticed, but they do not provide a complete map of agricultural suffering. Some communities may have experienced serious shortages, while others were buffered by climate, trade, wealth, or storage. The atmosphere imposed a broad disturbance, but the human result passed through an economic landscape already divided by geography and status. In northern Europe, the danger could be intensified by a short growing season. In the Mediterranean, another question becomes equally important. When nature reduced the reliability of production, how much protection could an interconnected society provide before its own networks began to feel the strain? Looking beyond Europe makes the events beginning in 536 both more convincing and more difficult to simplify. Natural archives from different areas of the Northern Hemisphere indicate that the climatic disturbance extended far beyond the Mediterranean or Scandinavia. Tree ring chronologies from regions of Asia contain evidence of unusually cold growing conditions during the middle 6th century, adding geographical depth to the broader pattern already visible in European records. Historical traditions from East Asia also preserve reports of unusual atmospheric or seasonal conditions during this general interval, although such texts must be dated and interpreted with the same caution applied to European chronicles. No single description should be treated as a thermometer, and similarities between distant writings do not prove that every observer witnessed exactly the same phenomenon. Their value increases when they are compared with independently dated natural archives. A tree growing in a cold, sensitive environment responds to temperature without knowing what any chronicler wrote. Ice accumulating thousands of kilometers away preserves atmospheric chemistry without knowing whether a harvest succeeded. When these records point toward disturbance during the same narrow span of years, they strengthen the argument for climatic forcing operating across a large geographical area. Yet a hemispheric signal is not the same thing as a uniform hemispheric disaster. Asia contained enormous environmental diversity in the 6th century, from northern forests and continental interiors to monsoon regions, high plateaus, river valleys, dry grasslands, and subtropical farming zones. The same change in atmospheric aerosols could interact differently with each of these environments. Temperature might dominate the response in one location, while precipitation changes mattered more elsewhere. Some agricultural systems depended heavily on summer warmth, others on the timing and strength of seasonal rainfall. Even neighbouring communities could therefore experience different outcomes from the same broad atmospheric disturbance. This geographical diversity mirrors one of the oldest facts of human history. As our species spread across the planet, humans did not survive by discovering one universal way to live. They adapted to local combinations of water, temperature, plants, animals, soils, and seasons. Agriculture increased those differences because crops and farming calendars became closely matched to regional environments. By the 6th century, farmers across Eurasia were not operating one shared food system. They cultivated different plants, managed different animals, relied on different rainfall patterns, and lived within political networks of very different size and structure. A cold summer that threatened grain maturation in a northern environment might not produce the same agricultural problem farther south. A change in rainfall could be more consequential than temperature in another region. This is why evidence for a broad volcanic climate disturbance cannot be converted into a single claim of worldwide crop failure. The physical forcing could cross borders, while human vulnerability remained local. Historical records also survive unevenly. Some societies left written chronicles that can be compared with climate evidence. Others are known mainly through archaeology or later textual traditions. Silence in the surviving record does not prove that nothing happened, just as a dramatic written account does not prove that an entire continent shared the experience it describes. Researchers therefore gain the clearest picture when they resist filling empty spaces with assumptions. The middle 6th century appears in multiple natural archives as an exceptional climatic interval, and volcanic forcing provides a strong mechanism linking many of those observations. What remains less certain is how those environmental changes translated into daily life across the vast range of societies affected by them. Some populations may have faced serious agricultural strain. Others may have benefited from local conditions, diverse food sources, trade, storage, or political organization. Many communities probably experienced mixtures of difficulty and recovery that left only faint traces. That unevenness does not weaken the importance of 536. It reveals the true scale of the problem. A disturbance large enough to alter climate across wide areas did not erase geography or culture. Instead, it entered thousands of different local systems, each with its own limits and protections. The pale sun described in one region, the narrow tree rings preserved in another, and the volcanic sulfates sealed in polar ice belong to the same environmental puzzle, but they do not justify one identical human story. The closer we come to reconstructing the physical event, the more clearly we must separate what happened to the atmosphere from what happened to every society beneath it. By the beginning of the 540s, many communities across the Northern Hemisphere had already lived through several years in which familiar environmental rhythms had become less reliable. The atmospheric disturbance around 536 had been followed by unusually cold summers in many regions, and another major volcanic eruption around 540 renewed the climatic pressure before recovery was complete. This does not mean that every population was hungry, weakened, or declining. Some areas may have maintained adequate harvests, some had access to trade or stored food, and some were buffered by local climates that reduced the severity of the shock. Yet repeated environmental stress can change the background conditions in which people live, even when no single year produces complete collapse. Reserves may be smaller, livestock numbers may recover slowly. Households that sold possessions or consumed seed during earlier shortages may have fewer choices later. Governments and landowners may still collect obligations from communities whose agricultural margins have narrowed. Markets can continue to function while food becomes more expensive for those with the least wealth. In this way, a population can remain socially organized and economically active while carrying less resilience than before. The human body also carries the memory of difficult seasons. Poorer diets do not affect everyone equally, and climate records cannot tell us who was malnourished. But prolonged insecurity can increase biological strain for some people. Physical labor still has to be performed. Children still need energy for growth. Pregnant people, older adults, and those already ill may face different nutritional demands. None of this proves that 6th century populations entered the 540s in a single condition of weakness. It shows only that repeated pressure can narrow the range within which individuals and communities absorb new problems. This principle reaches deep into human history. Our species survived earlier climatic shifts because people could move, share resources, change diets, and use social networks to spread risk. Agricultural and urban societies developed additional protections through storage, taxation, trade, and redistribution. But larger systems also created dependencies. A city that relied on grain arriving from distant provinces was resilient only while enough grain existed and transport continued. A household that relied on markets was protected only while food remained affordable. A state that depended on taxes and labor needed rural production to remain strong enough to support those demands. Environmental stress, therefore, did not simply weaken bodies. It could also place quiet strain on the systems that connected bodies to food. This matters when considering what happened in the 540s, because another kind of disaster was about to enter the historical record. It would be tempting to draw a straight line from volcanic cooling to epidemic disease, as if one event automatically produced the other. The surviving evidence does not justify that claim. Climate can influence ecosystems, food security, mobility, and human health, but the emergence and spread of an infectious disease depend on the biology of the pathogen, its hosts and vectors, patterns of movement, settlement, and many other conditions. Temporal overlap is not proof of direct causation. The climatic shocks beginning in 536 and the pandemic that appeared in the 542nd must therefore be treated as distinct processes that happened within the same historical generation. Their interaction is a legitimate question, but it must be separated from the stronger claim that one caused the other. What can be said with greater confidence is that the people who encountered the new epidemic were not living in an untouched world. Many had already experienced abnormal skies, cold summers, uncertain harvests, and repeated volcanic disturbances. Some communities had recovered well. Others may still have been rebuilding reserves or adjusting to changed economic conditions. The significance of this background is not that it predetermined the disaster to come. It is that human vulnerability is cumulative. A new shock always arrives in a world shaped by previous ones, and by the early 540s, the world into which epidemic disease would spread had already spent years adapting to environmental uncertainty. In the early 540s, a new crisis entered the 6th century world, one that was biological in a very different sense from failed crops or cold summers. Historical accounts describe a major epidemic spreading through territories connected to the Eastern Roman Empire, reaching Constantinople in 542 and continuing through repeated outbreaks over subsequent decades. Modern genetic research has added evidence unavailable to the people who recorded those events. DNA recovered from human remains at several early medieval burial sites has identified Yersinia pestis, the bacterium responsible for plague, confirming that the first pandemic of the historical era was not simply a vague collection of unrelated diseases. This matters because written descriptions alone cannot always identify ancient pathogens with certainty. Symptoms can overlap, terminology changes, and chroniclers wrote without modern microbiology. Ancient DNA provides an independent biological record, much as tree rings and ice cores provide independent environmental records. In this case, the evidence moves the investigation from descriptions of sickness toward the organism itself. Yet identifying the pathogen does not answer every question about how the pandemic began, how quickly it moved through every region, or why some places were affected more severely than others. Yersinia pestis has an ecological history involving animal hosts, vectors, human movement, and changing environments. The exact routes by which 6th century plague entered Mediterranean populations remain an active field of research, and the surviving evidence does not justify one simple story of origin. What is clearer is that the disease spread through a world already connected by ships, roads, trade, taxation, military movement, and dense settlements. These networks were sources of economic resilience, but they could also move people, animals, goods, and pathogens over distances far greater than an isolated village could manage. A port receiving grain from abroad might gain protection against local shortage while also maintaining connections through which infectious disease could travel. Such complexity is one of the recurring features of human history. From the earliest migrations of Homo sapiens, movement connected populations and carried biological consequences along with cultural exchange. As settlements became larger and trade routes longer, the scale of those connections increased. By the 6th century, imperial systems linked environments that no individual could see as a whole. Disease could therefore move through human networks in ways that resembled the earlier atmospheric shock, only in one limited sense. Its source and its local consequences could be separated by enormous distances. But plague and volcanic cooling were not the same phenomenon, and they should not be merged into a single cause. The eruption associated with 536 did not create Yersinia pestis. A volcanic aerosol veil cannot transform into a bacterium. The strongest evidence identifies the pathogen independently of the climatic events. The scientifically responsible question is narrower. Could environmental stress, ecological changes, food insecurity, movement, or altered human vulnerability have influenced the conditions through which plague spread or affected populations? Such interactions are possible in principle, but demonstrating them for the 6th century requires evidence rather than coincidence in dates. The appearance of plague only a few years after major volcanic disturbances is striking, yet chronology alone cannot prove causation. This restraint is especially important because the scale of the Justinianic Plague remains debated. Historical writers describe severe mortality in some cities and regions, but modern scholars continue to examine how representative those accounts were across the much larger Mediterranean and Eurasian world. Archaeological and demographic signals are uneven. The pandemic was real, and Yersinia pestis was present, but no single mortality percentage can safely describe every population it reached. For the people living through the 540s, however, the distinction between climate and disease would not have reduced the burden of facing them close together in time. Some communities had already experienced colder growing seasons and uncertain harvests. Then, a pathogen capable of causing deadly epidemics entered human networks. The important historical lesson is not that one disaster produced the other. It is that different systems can fail or become unstable within the same generation. The sky had changed first. The harvests had become less dependable in some regions. Now a microscopic organism, entirely separate from volcanic sulfur, was adding a new kind of pressure to the same human world. When two disasters occur within the same generation, it is natural to search for a single chain connecting them. The volcanic disturbances beginning around 536 were followed only a few years later by the first known pandemic of plague. And that closeness in time has encouraged researchers to ask whether climate and disease interacted. The question is reasonable, but it requires a distinction that is essential to understanding the 6th century. Events can overlap without one directly causing the other. They can also influence the conditions surrounding one another without forming a simple line of cause and effect. Yersinia pestis existed as a biological organism independently of the volcanic eruptions. The sulfur that entered the atmosphere did not create the bacterium, and cooler summers did not transform ordinary microbes into plague. The origin, maintenance, and spread of Yersinia pestis involved animal hosts, vectors, ecological conditions, and networks of movement whose history cannot be reduced to the climate shock of 536. At the same time, environmental change can alter ecosystems and human behavior. Shifts in temperature and rainfall can affect animal populations and vegetation. Food insecurity can influence migration, trade, labor, and the movement of supplies. Poor nutrition can place strain on some human bodies. These mechanisms make interactions scientifically plausible, but plausibility is not proof that a specific sequence occurred in a specific place. To demonstrate causation, researchers need evidence linking the environmental change to the ecological steps through which the pathogen was transmitted. For the 6th century, many of those steps remain uncertain. This is why timing alone cannot carry the argument. A major eruption around 536, another around 540, and plague appearing in the Mediterranean world during the early 540s form a striking chronology, but chronological proximity does not show that the first produced the last. Human history contains many events that happen close together because societies are always experiencing several processes at once. Political conflict, trade, migration, agriculture, disease, and climate operate on overlapping timescales. The challenge is to understand their interactions without forcing them into one explanation. This problem reaches far beyond the 6th century. Throughout human evolution, climate changes altered landscapes while pathogens, competitors, and social relationships changed independently. A drought could influence where people moved without being the sole reason for migration. A cold period could reduce food availability without directly causing a particular infection. Human survival has always depended on navigating several pressures simultaneously, rather than responding to one isolated variable. The same principle applies to complex societies in late antiquity. A community facing plague might also be recovering from weak harvests, paying taxes, dealing with warfare, or receiving migrants. Another community might encounter the pathogen after several productive seasons and possess stronger reserves. The disease remained the same bacterium, but the social and biological context into which it arrived could differ. This is where the idea of cumulative vulnerability becomes useful, as long as it is not turned into certainty. Earlier climatic stress may have reduced resilience for some populations, while others may have recovered or remained comparatively protected. Trade networks that brought food into cities could also connect distant populations through movement, but whether those networks played a particular role in plague transmission must be established from historical, archaeological, ecological, and genetic evidence. No single factor should be assumed to explain the pandemic's path. Ancient DNA has greatly strengthened what can be said because it confirms the presence of Yersinia pestis in 6th century victims. Climate proxies have independently strengthened the reconstruction of volcanic cooling. Keeping those evidence streams separate at first is precisely what allows their possible relationship to be studied responsibly. If they are merged too early, coincidence can be mistaken for cause. If they are never compared, potentially important interactions can be missed. The most reliable picture, therefore, lies between those extremes. The middle 6th century was a period in which major volcanic forcing, agricultural pressure in some regions, political and economic systems, and epidemic disease overlapped within the lives of the same generations. Each had its own mechanisms. Together they could create conditions more difficult than any one shock considered alone. The significance of 536 is not that it secretly caused everything that followed. It is that it marked the beginning of an unusually demanding environmental sequence, and the people living through that sequence soon encountered a second disaster whose biological cause was entirely different. In 2024, researchers added a new piece of evidence to the story of the 6th century climate shock by studying archaeological oak from Denmark. By then, tree ring chronologies from other regions, ice cores, and historical records had already established that the middle of the 6th century contained an exceptional sequence of volcanic and climatic disturbances. What the Danish material offered was something different, another independent archive from a landscape where people had actually cut and used the wood. Researchers assembled 654 oak samples recovered from archaeological excavations and built tree ring chronologies covering centuries around the event. Because the rings could be cross-dated year by year, the investigators could ask whether Danish trees responded at the same moments already identified elsewhere. At the national level, growth dropped sharply in 536 and again around 539, while eastern and western Denmark did not respond in exactly the same way. In eastern Denmark, the strongest reduction appeared around 540. Some individual site chronologies did not show an equally dramatic decline at all. That variation is scientifically useful. If every tree were forced into one identical pattern, the result would look simpler but would tell us less about how real landscapes work. Soil conditions, moisture, local temperature, tree age, and regional weather can change how a forest responds to the same broad climatic disturbance. The Danish study therefore strengthened the larger picture precisely because it preserved both agreement and difference. The major years of reduced growth aligned with the volcanic sequence already known from other northern records, while local chronologies reminded researchers that climate effects are never perfectly uniform. This kind of evidence is especially valuable for human history, because archaeological timber occupies an unusual position between natural archive and human activity. The trees grew under environmental conditions, but people later selected, cut, transported, and used the wood. A beam or timber can therefore preserve biological information from a landscape that also supported human communities. Yet that does not mean every change in the archaeological wood record can be translated directly into a social crisis. The researchers also examined patterns in tree felling, hoping to see whether climate disturbance might have influenced human use of timber. The available material did not support a clear link between the mid-6th century climatic event and changes in felling activity. Earlier gaps in the archaeological wood record made such an interpretation especially uncertain. This negative result matters. Science advances not only when evidence confirms a dramatic idea, but also when data show where the argument must stop. The oak rings provide strong evidence of growth stress. They do not prove that Danish communities suddenly stopped building, abandoned settlements, or changed their behavior because of the volcanic shocks. That distinction connects directly to the longer human story. For thousands of years, people have lived inside environments whose biological productivity changes from season to season. Archaeology can sometimes preserve the materials they used, but those materials must be interpreted carefully. A narrow ring tells us about a tree's growth. A felling date tells us when that tree was cut. Neither one, alone, tells us why a family moved, why a settlement changed, or how much food a community possessed. The strength of the 2024 Danish study lies in adding another independently dated record to a pattern already seen across the Northern Hemisphere. It shows that oaks growing in Denmark registered major stress around the same years that volcanic sulfate appears in ice and severe cooling appears in other tree ring reconstructions. It also shows that local responses varied and that evidence for direct changes in human timber use was not strong enough to support a confident claim. That combination of confirmation and restraint is exactly what makes new evidence valuable. The story of 536 becomes clearer, not because one discovery suddenly proves everything, but because more independent records continue to agree on the physical disturbance while also defining the limits of what we can say about the people who lived through it. A dramatic discovery can change a headline, but a reliable reconstruction of the past is usually built more slowly. The new Danish oak record matters because it joins evidence already pointing in the same direction. Long before those archaeological timbers were analysed as a large data set, researchers had identified unusually weak tree growth in other northern regions, major volcanic sulfate deposits in polar ice, and historical descriptions of diminished sunlight during the middle of the 6th century. None of those records was created to confirm another. Trees responded to environmental conditions. Snow captured atmospheric material. Chroniclers described what they believed they saw. Archaeological wood survived because people cut and used it. When these independent archives converge around the same narrow sequence of years, the probability that the pattern comes from one local accident becomes smaller. This is why scientific confidence often grows through replication rather than spectacle. A new dataset does not need to overturn everything previously known. It can strengthen a conclusion by testing whether the same signal appears in another place, another archive, or another method. It can also reveal where the earlier picture was too simple. The Danish oaks did both. Their growth reductions broadly align with the climatic disturbance associated with 536 and the renewed shock around 539 to 540, yet regional differences within Denmark show that neighbouring landscapes did not respond identically. That combination of agreement and variation is what scientists expect from a large climatic forcing acting through local environments. If a volcanic aerosol veil reduces incoming solar energy across a wide region, temperature-sensitive trees may show stress, but rainfall, soil, exposure, and local weather still shape the magnitude of that stress. The same principle applies when natural evidence is compared with human history. One climatic signal may be broad, while social consequences remain uneven. A settlement with stored food, livestock, coastal resources, or strong exchange networks may absorb a poor growing season differently from one with fewer alternatives. This pattern reaches back through the history of our species. Human survival has never depended on removing environmental variation. It has depended on responding to it. From mobile foragers to agricultural communities and later urban societies, people created buffers through movement, storage, exchange, technology, and cooperation. Modern science reconstructs ancient shocks in a similar way, not by trusting one clue, but by combining many forms of information so weaknesses in one record can be checked against strengths in another. Tree rings can provide annual precision but do not identify every atmospheric cause. Ice cores preserve volcanic chemistry, but do not reveal what every harvest produced. Historical texts preserve human observation but are geographically uneven and shaped by transmission. Archaeology can reveal changes in settlement and material use, but rarely supplies a simple explanation for why those changes occurred. When these are treated as different witnesses rather than forced into one story, the reconstruction becomes more secure. This is also why the phrase "new proof" can be misleading if it suggests that one recent study suddenly settled the entire mystery of 536. The more accurate picture is cumulative. New evidence sharpens chronology, expands geographical coverage, tests earlier interpretations, and sometimes removes claims that cannot be supported. The Danish oak study is valuable because it strengthens the climatic signal while refusing to claim a clear change in timber harvesting where the data do not justify one. That restraint is not a disappointment. It is evidence that the method is working. Science becomes more trustworthy when it tells us both what the records support and where they fall silent. The year 536 is increasingly visible because independent archives continue to overlap. Unusual sunlight in written memory, reduced growth in trees, volcanic sulfur in ice, and climate reconstructions showing severe cooling. No single archive contains the whole event. Together they create something stronger than one dramatic discovery, a pattern that survives repeated attempts to test it from different directions. The closer those independent records come to agreement, the less the story depends on any one witness, and the more confidently we can separate a real environmental shock from the exaggerations later generations might place around it. The evidence for a major climatic disturbance, beginning in 536, is now strong, but several important questions remain open. The first is surprisingly basic. Researchers still cannot identify the volcano responsible for the initial eruption with complete confidence. Ice cores preserve sulfate from the event, and microscopic volcanic particles can sometimes provide chemical fingerprints, yet matching those traces to a specific eruption requires suitable material from both the ice and candidate volcanoes. Several possible sources have been discussed, but no single identification has achieved the certainty needed to close the question. This does not weaken the conclusion that a major eruption occurred. It separates what the evidence establishes from what it has not resolved. A second uncertainty concerns geography. Climate reconstructions show severe cooling across large areas of the Northern Hemisphere, but the magnitude was not identical everywhere. Mountains, coastlines, oceans, prevailing winds, rainfall patterns, and local ecosystems all influence how a broad atmospheric disturbance is expressed on the ground. Even tree ring records from nearby regions can show different levels of growth stress. Researchers therefore cannot take a reconstruction from one forest and assume that a community hundreds of kilometers away experienced the same conditions. The same caution applies to harvests. A narrow tree ring may indicate a difficult growing season for a temperature-sensitive tree, but it does not directly measure grain yield, livestock survival, food prices, or household nutrition. Each step from atmosphere to society requires additional evidence. This is where the history of human adaptation becomes important. Humans have always lived inside environments that vary across short distances. Two communities exposed to the same cold season may respond differently because they possess different foods, technologies, social networks, institutions, or opportunities to move. Agriculture increased the importance of local conditions by tying crops to soils and seasonal calendars, while trade and state organization created new ways to spread risk. For the 6th century, those human systems are often harder to reconstruct than the climate itself. Archaeological settlements may be abandoned, reorganized, or rebuilt for many reasons. Burial patterns can change because customs changed, not only because population declined. Written sources may emphasize crises because unusual events attracted attention, while ordinary years leave fewer vivid descriptions. Even when climate stress and social change occur near one another, chronology alone does not demonstrate that the first caused the second. The uncertainty surrounding human consequences is not a gap to be filled with dramatic assumptions. It is information about the limits of the surviving record. Scientists can say with increasing confidence that volcanic aerosols altered the atmosphere, that summers cooled sharply in many northern regions, and that another major eruption around 540 renewed the disturbance. They can compare those signals with archaeological and historical evidence from societies living through the same decades. What they cannot yet do is reconstruct one universal sequence in which dim sunlight caused a specific harvest loss, which caused a precise population decline, which then produced every political change that followed. The world of 536 was too diverse for such a chain. New datasets may narrow some uncertainties. Better chemical matching could identify the source volcano. Additional tree chronologies may reveal regional patterns with greater precision. Ice core dating can continue to be refined, while archaeology can show how communities changed across the same years. New methods may allow records from different disciplines to be compared more closely. Yet greater precision will probably make the story more complex rather than simpler. Some claims may become stronger, while others may disappear. That is the normal movement of research. The strongest conclusion about 536 is not that every mystery has been solved. It is that independent archives have transformed extraordinary ancient descriptions into a well-supported climatic event while preserving clear boundaries around what remains unknown. Those boundaries distinguish reconstruction from legend. We now understand far more about why the 6th century sky changed than the people beneath it ever could. But the identity of the first volcano, the exact regional consequences, and the full scale of human responses remain questions the surviving evidence has not completely answered. By the time the evidence is assembled across disciplines, several conclusions about 536 become difficult to dispute. Something extraordinary happened to the atmosphere in the middle of the 6th century. Historical observers described a sun that seemed strangely weakened. Tree rings from multiple regions record unusually poor growth and severe summer cooling. Ice cores preserve large deposits of volcanic sulfate near the same interval, followed by another major volcanic signal around 540. These records were created by entirely different processes, yet they converge on the same broad sequence. That convergence is the foundation for what can be said with confidence. A major volcanic eruption, or possibly a closely timed sequence associated with the first disturbance, injected enough sulfur into the upper atmosphere to alter incoming solar energy and contribute to sharp cooling across large areas of the northern hemisphere. A second major eruption a few years later renewed the forcing before the climate system had fully recovered. The exact identity of the volcano responsible for the first event remains unresolved, but uncertainty about its name is not uncertainty about the atmospheric disturbance itself. The physical mechanism is well understood. Sulfur gases reaching the stratosphere can form sulfate aerosols that scatter sunlight and cool the surface for a limited time. When strong eruptions occur close together, their effects can overlap with slower responses in oceans, snow, sea ice, and atmospheric circulation, helping explain why the climatic consequences extended beyond one strange summer. What cannot be stated with the same certainty is that every society experienced identical hardship. Climate reconstructions reveal regional variation. Historical records survive unevenly. Archaeology does not provide one universal signal of abandonment, famine, or demographic collapse. A narrow tree ring is evidence of biological stress in a tree, not a direct measurement of human hunger. A sulfate layer in Greenland or Antarctica identifies volcanic material in the atmosphere, not the number of people who died in a village. These distinctions matter because the strongest account of 536 does not need exaggeration. Its significance survives careful limits. The event altered the environmental conditions on which many human communities depended, especially where agriculture operated close to climatic thresholds. Cooler growing seasons could reduce crop productivity, narrow food reserves, and make recovery more difficult when another unfavorable season followed. But storage, livestock, fishing, trade, wealth, political organization, and local ecology could change the outcome dramatically from one place to another. This pattern belongs to the much longer history of our species. Humans have repeatedly survived environmental change not because climate became irrelevant, but because behavior, cooperation, mobility, technology, and social networks created alternatives. By the 6th century, those alternatives had become more complex, yet they still rested on biological foundations. Grain required a growing season, animals required pasture and fodder, cities required food produced elsewhere. States could redistribute surplus, but they could not manufacture harvests independently of the environment. That is why the climatic shock mattered, even without a universal catastrophe. It reduced reliability in systems built around seasonal expectations. The later arrival of plague added another severe pressure, but ancient DNA identifies Yersinia pestis as a separate biological cause, and the volcanic events should not be presented as the direct origin of that pandemic. The strongest reconstruction, therefore, contains both certainty and restraint. We can say that major volcanic forcing darkened or weakened sunlight, as perceived in some regions, sharply cooled many northern summers, affected biological growth, and was followed by another powerful eruption around 540. We can say that these disturbances created serious risks for agricultural societies and contributed to a broader period of climatic instability. We cannot say that every harvest failed, every population starved, or every political transformation was caused by the climate. The evidence makes 536 extraordinary without requiring it to become a legend. Modern research has made the year more remarkable by replacing a mysterious ancient report with a testable physical history assembled from ice, wood, chemistry, climate, archaeology, and written memory. Calling 536 the worst year to be alive is powerful because it compresses a complicated historical crisis into a question anyone can understand. But it is not a scientific ranking. There is no complete dataset that allows historians to compare every year in human history and measure suffering with one common scale. Different centuries produced different dangers. Warfare, epidemic disease, famine, displacement, political collapse, and environmental shocks, often affecting some regions severely while leaving others relatively protected. Even within the year 536, the experience of a farmer in northern Europe could have been very different from that of a merchant in the eastern Mediterranean, or a community living far beyond the regions preserved in written sources. The phrase, therefore, works best as a historical frame for understanding how unusual the conditions were, not as a literal claim that every person alive suffered more than people in any other year. What makes 536 stand out is the unusual combination of evidence and vulnerability. Contemporary writers described weakened sunlight, trees recorded severe growth stress, ice preserved volcanic sulfate. Climate reconstructions indicate exceptionally cold summers across many northern regions. Another major eruption around 540 renewed the disturbance, extending environmental pressure into the years that followed. For societies dependent on seasonal agriculture, these were not abstract changes in temperature. They could alter the length of the growing season, the reliability of harvests, the amount of food stored, and the capacity to recover before another difficult year arrived. Yet suffering still depended on where someone lived and what resources surrounded them. A household with grain reserves, livestock, relatives, or access to trade might survive conditions that were devastating to a household without those protections. A port could receive food from distant regions. A village could supplement crops with fishing or herding. Wealth could purchase time. Political systems could redistribute resources, although not always equally. The same environmental shock therefore passed through layers of geography, economy, and social status before reaching individual lives. That pattern is deeply familiar in human history. Our species has endured climatic instability for tens of thousands of years, but people have never experienced environmental change as identical biological units. Culture creates differences in exposure. Technology changes options. Cooperation can spread risk. Inequality can concentrate it. Agriculture and urban life increase the number of people who could be supported by productive landscapes, while also making large populations dependent on predictable flows of food and energy. In 536, that predictability was disturbed across a strikingly wide area. This is why the year remains such a useful symbol even if the superlative cannot be proven. It represents a moment when something normally taken for granted, the dependable appearance and warmth of the sun, became uncertain, and when the consequences moved from atmosphere to plants, harvests, stores, markets, and human bodies. The later arrival of plague makes the broader decade appear even more severe, but it should not be retroactively folded into the claim that everything terrible began in one year. The pandemic had its own biological cause. Political conflicts had their own histories. Regional transformations followed different paths. Nor do surviving sources allow us to compare psychological fear, hunger, disease, violence, and displacement as if they were equivalent measurements. Human suffering cannot be reduced to one score, especially when evidence is far richer for some societies than for others. The phrase worst year becomes misleading when it turns all of those processes into consequences of a single event. Used carefully, however, it points toward a more defensible idea. For many people living in regions strongly affected by the climatic shock, 536 may have marked the beginning of an exceptionally difficult sequence, whose scale they could not understand, and whose source they could not see. Its historical importance lies not in winning a contest of misery, but in showing how quickly ordinary expectations can become unreliable when natural systems shift beyond the range a society has prepared to absorb. The deepest lesson of 536 is not that civilization is fragile in a simple or inevitable way. It is that even complex societies remain connected to physical systems they cannot fully control. The 6th century world contained cities, states, long-distance trade, taxation, armies, farms, ports, religious institutions, and generations of accumulated knowledge. None of that disappeared when the sky dimmed. People continued working, trading, planting, traveling, governing, raising children, and adapting. Yet beneath those institutions remained basic dependencies that had shaped human life for far longer than cities had existed. Plants needed light and suitable temperatures. Animals depended on vegetation. Harvests depended on seasons. Human bodies depended on food. When volcanic aerosols altered the atmosphere, the disturbance moved through those relationships without needing to destroy a society directly. Its effects were filtered through geography, wealth, storage, technology, trade, and human decisions. That is why the story is neither one of automatic collapse nor one of complete resilience. It is a story about margins. A community with surplus can absorb a poor season. A network with several sources of food can compensate when one fails. Families can share, governments can redistribute, merchants can redirect supplies, and people can change behavior. But every buffer has limits, especially when another shock arrives before recovery is complete. This principle connects 536 to the much longer history of our species. Human beings survived ice age fluctuations, droughts, migrations, changing coastlines, and ecological transitions because flexibility became one of our greatest strengths. We learned to cooperate, store knowledge, diversify diets, build tools, move resources, and organize beyond immediate kin. Agriculture and urban life expanded those abilities, but they did not remove dependence on climate and ecology. They transformed that dependence into larger systems. A city could be protected from a local crop failure by grain arriving from far away, yet that protection still required productive land somewhere, functioning transport, and enough surplus to move. Complexity can therefore create resilience and vulnerability at the same time, because the systems that protect people during ordinary hardship may themselves depend on conditions that a larger environmental shock can disturb. The reconstruction of 536 carries another lesson as well. No single kind of evidence is sufficient. Written accounts preserve human experience but can exaggerate, omit, or misunderstand causes. Tree rings record biological growth but do not tell us what every farmer harvested. Ice cores reveal atmospheric chemistry but cannot describe a household's hunger. Archaeology shows material change without always explaining why it occurred. Ancient DNA can identify a pathogen while remaining silent about every condition that shaped its spread. When these records are compared carefully, each corrects the others. The result is slower than a dramatic story, but far more durable. That method has transformed 536 from an ancient report of a strangely weakened sun into one of the clearest examples of how natural archives can recover environmental events that no observer understood at the time. It also leaves uncertainty where uncertainty belongs. We still do not know the first volcano with complete confidence. We cannot calculate one universal harvest loss or death toll. We cannot attribute every migration, conflict, or political transformation of the era to climate. Those limits are not weaknesses in the story. They are what's separate evidence from legend. The people of 536 could see the pale light above them, but they could not see sulfur circulating high in the atmosphere, nor the chemical traces that would remain frozen for centuries. They could experience cold summers without knowing that trees across distant landscapes were recording the same disturbance. Today, those scattered records can be brought together, allowing us to understand a crisis that its survivors could only endure. And perhaps that is the enduring question left by 536. When the systems beneath ordinary life begin to change in ways we cannot immediately see, how quickly can a civilization recognize what is happening before the strain reaches the people depending on it?